Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into Earth's earliest days, when our world spun beneath not one moon, but two. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. 4.5 billion years ago, the solar system writhes in the final throes of its formation. A sprawling disk of dust and gas and rocky debris that extends far beyond the orbit of what will someday become Neptune. The young sun burns at the center of this cosmic maelstrom, barely 50 million years old. Its nuclear furnace still learning the rhythms that will sustain it for 10 billion years. Around this infant star, gravity performs its slow work of accumulation, gathering the scattered detritus of stellar birth into ever larger clumps that will eventually become the worlds we know today. Earth exists in this primordial chaos, but not as the blue marble suspended against black space that astronauts will photograph from lunar orbit billions of years in the future. This early Earth spins rapidly through its abbreviated day, completing one full rotation in perhaps 6 hours, while its surface remains entirely molten. A sphere of liquid basalt and iron beneath skies thick with steam and carbon dioxide. No solid ground exists anywhere on the planet. No oceans cool its surface. No atmosphere offers protection from the cosmic radiation that streams outward from the sun's corona. The entire inner solar system seethes with violence that operates on scales incomprehensible to minds evolved to navigate the brief spans of biological time. Mountain-sized asteroids streak through space at velocities measured in kilometers per second, their impacts releasing energy equivalent to thousands of nuclear weapons. Comets arrive from the outer reaches of the solar system, trailing tails of ice and dust that glow in the solar wind. Protoplanets the size of modern-day Mercury wander through orbits that carry them into collision courses with their neighbors, shattering both worlds and scattering their fragments across millions of cubic kilometers of space. The planet-building process unfolds with the patience that only geological time can provide, each collision adding mass and momentum to the growing worlds. Some of these early planets grow large enough to hold onto atmospheres of hydrogen and helium, captured directly from the solar nebula. Others develop thick crusts of solid rock that crack and reform under the constant bombardment from space. Many more shatter completely against their neighbors, their constituent materials dispersed into asteroid belts that will orbit the sun for billions of years, waiting to be swept up by the next generation of planetary formation. Among these wandering protoplanets moves one that modern scientists have named Theia, after the Greek Titaness who mythology claims gave birth to Selene, the moon goddess. Theia measures roughly the size of Mars, massive enough to have undergone the process of differentiation that separates heavy elements from light ones, creating a dense iron core surrounded by a mantle of silicate rock for perhaps 20 million years. This world follows an orbital path that carries it through the same region of space occupied by the young Earth. The two bodies locked in what astronomers term a resonant relationship. Gravitational resonances represent one of the most elegant phenomena in celestial mechanics. Patterns of orbital motion that emerge when two or more bodies exert regular, periodic influences upon each other's paths through space. In Theia's case, the protoplanet likely occupies one of Earth's Lagrange points, regions of space where the combined gravitational pulls of the Sun and Earth create pockets of relative stability. These gravitational balance points allow smaller bodies to share Earth's orbital path around the Sun, trailing 60 degrees ahead of or behind the planet in its yearly journey. For millions of years, this delicate balance holds. Theia and Earth maintaining their cosmic dance while the solar system continues its violent process of consolidation. Occasionally, gravitational perturbations from Jupiter or the other gas giants nudge one or both worlds slightly from their prescribed paths. But the resilience of orbital mechanics quickly restores the equilibrium. The two planets continue their separate existences, each accumulating mass from the debris that still litters the inner solar system, each growing larger and more gravitationally influential with every passing millennium. No consciousness witnesses this slow approach, for life itself remains nothing more than a theoretical possibility. Complex chemistry waiting for the right combination of temperature and pressure and chemical gradients to begin its first tentative experiments in self-replication. The solar system contains only the raw materials of geology and astronomy, matter and energy playing out their interactions according to the fundamental forces that govern the behavior of everything from subatomic particles to galactic clusters. The young sun burns with an intensity 25% dimmer than the star that will warm the Earth during humanity's brief moment in geological time. But even this reduced luminosity proves sufficient to drive complex atmospheric chemistry on both worlds. Solar radiation strips electrons from atoms in the thin atmospheres, creating charged particles that spiral along magnetic field lines and generate aurora that paint the skies in colors no eye will see for billions of years. Solar wind sculpts the magnetospheres of both planets, compressing them on the dayward side and stretching them into long tails that extend millions of kilometers into space. Earth's magnetic field during this epoch remains weak and chaotic, generated by convection currents in its molten iron core, but lacking the stability that will eventually protect the planet's atmosphere from erosion by solar wind. The field lines twist and reconnect in patterns that change over timescales of decades or centuries, occasionally reversing polarity entirely and leaving the planet temporarily vulnerable to cosmic radiation. During these periods of magnetic weakness, the solar wind strips away portions of the atmosphere, carrying water vapor and other volatile compounds into the emptiness of interplanetary space. The surface temperature on both worlds hovers near the melting point of basaltic rock, heated by multiple sources of energy that operate simultaneously across the globe. Radioactive decay in the planetary cores releases heat equivalent to thousands of volcanic eruptions every day. The gravitational compression of matter during planetary accretion converts kinetic energy into thermal energy, keeping the mantles molten and convecting. Most dramatically, the constant bombardment of asteroids and comets delivers impact energy that regularly resurfaces entire continents, erasing any geological features that might have begun to form during brief periods of relative calm. This bombardment represents the final phase of planetary formation, the period that geologists call the late heavy bombardment, when the last wandering debris from the solar system's formation rains down upon the terrestrial worlds. Evidence for this ancient catastrophe survives in the heavily cratered highlands of the Moon, where impacts from 4 billion years ago remain preserved in airless perfection. Similar cratering must have occurred on Earth and Theia during the same period, but the geological activity of larger worlds has long since erased most traces of this cosmic violence. Scientists studying lunar samples brought back by the Apollo missions discover isotopic evidence of this shared history, written in the chemical composition of highland rocks that formed during the solar system's youth. The ratios of oxygen isotopes in lunar basalts match those found in Earth's mantle with a precision that suggests the two worlds formed from the same reservoir of materials, in the same region of the solar nebula under nearly identical conditions. This isotopic fingerprinting provides some of the strongest evidence for the giant impact theory of lunar formation, supporting computer models that show how a Mars-sized impactor could have blasted sufficient material into Earth orbit to form the Moon. The mystery surrounding lunar formation has puzzled natural philosophers since ancient times. When Greek astronomers first calculated the Moon's distance and realized that it must be a substantial world in its own right rather than a mere point of light in the night sky. Throughout the 20th century, astronomers proposed 3 primary mechanisms for lunar formation: co-accretion from the same disk of material that formed Earth, capture of a wandering body that formed elsewhere in the solar system, or fission of material from Earth's rapidly rotating molten surface during the planet's earliest days. Each theory possessed certain attractive features but failed to explain crucial aspects of the Earth-Moon system. As Theia continues its inexorable drift toward gravitational instability, the stage becomes set for an event that will resolve these scientific puzzles while creating new mysteries that will perplex astronomers for decades to come. The gravitational interaction between Earth and its approaching visitor begins to deform the shapes of both worlds, raising tides in their molten surfaces that stretch hundreds of kilometers into space. The mathematical inevitability of orbital mechanics governs every aspect of this approach. Each body locked into trajectories determined by laws of physics that operate with perfect consistency across the vast emptiness of space. Only 20 million years separate this moment from the collision that will scatter debris across the inner solar system and fundamentally alter the composition and structure of both worlds. In cosmic terms, barely the blink of an eye. In human terms, 4,000 times longer than the entire span of recorded history. Soon, very soon in geological terms, Theia and Earth will meet in an impact that releases more energy than the Sun produces in an entire year, creating not just one moon but briefly, two. The approach accelerates with mathematical precision, 20 million years collapsing into 10 million, then 5, then 1. As gravitational perturbations finally destabilize the delicate orbital dance that has persisted since the solar system's youth. Theia drifts inward from its Lagrange point like a cosmic pendulum, swinging toward its inevitable collision with destiny. The protoplanet's trajectory carries it on a path that will intersect Earth's orbit at a grazing angle, neither head-on nor glancing, but somewhere between the two extremes that will prove crucial to the outcome of their meeting. Computer simulations running on modern supercomputers reveal the exquisite sensitivity of planetary formation to initial conditions. How tiny variations in velocity or angle of approach can determine whether two colliding worlds merge completely, shatter into fragments, or transfer just enough material to create satellite systems. In Theia's case, the impact parameters fall within a narrow range that astronomers call the Goldilocks zone of giant impacts. Not too violent to destroy both planets, not too gentle to fail in creating a substantial moon, but just energetic enough to blast material into Earth orbit while preserving the bulk of both worlds. The final million years of approach unfold with agonizing slowness. Theia's orbit decaying as tidal forces between the two worlds dissipate orbital energy through the constant flexing and heating of their molten interiors. Each world raises massive tides in the other, bulges of liquid rock that follow the gravitational pull like metallic waves hundreds of kilometers high. These tidal bulges lag slightly behind the direct line connecting the two planets, creating a torque that gradually robs Theia of orbital velocity and draws it ever closer to its massive companion. During this final approach, both planets undergo dramatic changes in their internal structure and surface conditions. The tidal heating generated by their gravitational interaction drives volcanic activity on scales unknown in the modern solar system, with eruptions that dwarf anything recorded in human history. Vast calderas open in the crusts of both worlds, venting superheated magma and volatile gases into space. The young Earth's surface, already molten from the energy of its formation and radioactive decay, becomes even more fluid as tidal forces pump additional heat into its interior. Theia experiences even more dramatic changes, its smaller mass making it more susceptible to tidal disruption. The protoplanet begins to elongate along the Earth-Theia axis, stretching like molten taffy under the inexorable pull of its larger neighbor. Computer models suggest that, by the time of impact, Theia may have already begun to break apart, its leading edge pulled away from the main body by Earth's overwhelming gravitational field. This pre-impact fragmentation will prove crucial to the eventual formation of multiple satellites rather than a single large moon. The atmospheres of both worlds thicken dramatically during this period. fed by the constant outgassing from unprecedented levels of volcanic activity. Steam rises from the magma oceans in quantities sufficient to shroud both planets in thick clouds that glow with the infrared radiation of superheated rock below. These early atmospheres consist primarily of water vapor, carbon dioxide, and sulfur compounds, with trace amounts of hydrogen and helium captured from the solar wind during brief periods when the magnetic fields of both worlds weaken under tidal stress. Solar radiation during this epoch remains about 25% weaker than the modern sun will eventually provide. But the greenhouse effect created by the thick atmospheric blankets surrounding both worlds more than compensates for the reduced stellar input. Surface temperatures on both planets climb well above the melting point of most silicate minerals, ensuring that no solid crust can form despite the constant cooling effect of radiative heat loss to space. The entire surfaces of both worlds remain in a state of dynamic equilibrium between melting and solidification, with local temperatures fluctuating by hundreds of degrees as tidal forces drive massive convection currents through the molten rock. The magnetic fields of both planets become increasingly chaotic as the tidal stresses disrupt the convection patterns in their molten iron cores. Earth's magnetosphere, already weak and unstable during this epoch, begins to fluctuate wildly as the core dynamo struggles to maintain coherent field lines under the influence of Theia's gravitational perturbations. Solar wind particles penetrate deeper into the magnetosphere during these periods of magnetic weakness, stripping away portions of the atmosphere and creating aurora displays that extend from pole to pole across both worlds. Theia's magnetic field, generated by a core only half the size of Earth's, proves even more vulnerable to disruption as the protoplanet stretches under tidal stress. Its core becomes elongated and develops complex circulation patterns that generate magnetic fields with multiple poles and frequent reversals. These magnetic anomalies create pockets of space around Theia, where charged particles from the solar wind can penetrate directly to the surface, heating the already molten rock to even higher temperatures. The final 1,000 years before impact bring changes visible even from the outer solar system. If any observer existed to witness them, both worlds glow with the infrared radiation of superheated rock, their thermal signatures bright enough to be detected by sensitive instruments across interplanetary distances. The gravitational interaction between Earth and Theia creates a complex pattern of orbital resonances that affects the motion of asteroids and comets throughout the inner solar system. Some bodies receiving gravitational kicks that send them spiraling toward the sun, others scattered outward toward the asteroid belt or beyond. The debris already orbiting both planets from countless earlier impacts begins to coalesce into temporary ring systems as the changing gravitational fields sort particles by size and orbital velocity. These proto-rings consist primarily of molten droplets of rock that solidify into spherical beads as they cool in the vacuum of space. Many of these particles will survive the coming collision to become incorporated into the lunar highlands, carrying within their crystal structure a record of the conditions existing in Earth orbit during the final days before impact. As the separation between the two worlds shrinks below 100,000 kilometers, roughly 1/4 the distance between Earth and the modern Moon, tidal forces begin to overcome the structural integrity of both planets' crusts. Massive fractures open across their surfaces, venting magma and gas in eruptions that reach velocities approaching escape velocity. Some of this material escapes the gravitational influence of both worlds entirely, forming a tenuous cloud of debris that extends millions of kilometers into space and will eventually be swept up by the other terrestrial planets or lost to the outer solar system. The final hours before impact unfold with the slow-motion inevitability of a landslide viewed from a great distance. Theia, now visibly elongated and partially fragmented, approaches Earth at a velocity of 11 kilometers per second, fast enough to circle the modern Earth in less than 4 hours, but glacially slow by the standards of cosmic catastrophe. The impact point lies in what will someday become the Pacific Ocean Basin. Though no ocean exists yet to receive the cosmic visitor, only an endless expanse of molten basalt beneath skies thick with steam and volcanic ash. Computer models running thousands of impact simulations reveal that this collision will unfold over the course of several hours, beginning with the first contact between Theia's leading fragments and Earth's atmosphere and ending only when the last debris settles into stable orbits around the newly formed Earth-Moon system. The impact will release energy equivalent to about 2 billion times the explosive yield that ended the Cretaceous period and the reign of the dinosaurs, enough to vaporize Earth's oceans if any existed and to melt the planet's crust to depths of hundreds of kilometers. Yet from this cosmic violence will emerge something unexpected and beautiful. Not one moon, but two. Both worlds destined to share Earth's sky for millions of years before their own gravitational interaction writes the final chapter of this ancient story. The smaller of these satellites, born from the trailing fragments of Theia's disrupted core, will follow Luna through the darkness of space until tidal forces draw them together in a collision that reshapes the lunar surface and creates the highland regions that still reflect sunlight across 4 billion years of geological time. Only hours now separate this moment from the impact that will scatter molten rock across the inner solar system and give birth to the Earth-Moon system that will endure until the sun itself swells into a red giant and strips away the atmospheres of the inner planets. So little time remaining, and yet so much about to change forever. The collision unfolds across several hours of geological violence that reshapes both worlds and scatters debris throughout the inner solar system. Theia's leading fragments, already stretched and partially molten from tidal stress, strike Earth's thick atmosphere at 11 kilometers per second, compressing the gas ahead of them until it glows white-hot with temperatures exceeding those found in stellar cores. The atmosphere itself becomes a weapon, its compressed shock waves racing ahead of the impactor to begin the process of planetary destruction even before solid matter makes contact with solid matter. When Theia's main mass finally strikes Earth's molten surface, the impact releases energy equivalent to 100 million hydrogen bombs, detonating every second for an entire day. The collision point vaporizes instantly, creating a fireball that expands outward at velocities approaching orbital speed and temperatures hot enough to dissociate rock into its constituent atoms. Shockwaves propagate through both planets at 20 kilometers per second, faster than sound travels through air, carrying enough energy to melt solid rock thousands of kilometers from the impact site. The physics of giant impacts operates on scales that dwarf terrestrial experience, governed by the same principles that shape stellar explosions and galactic collisions. When two planetary masses meet at cosmic velocities, the kinetic energy of motion converts entirely into heat and pressure, creating conditions briefly more extreme than those found in the cores of stars. Both Earth and Theia cease to exist as discrete worlds during the first minutes after contact, their separate identities lost in a common envelope of superheated plasma that extends far beyond either planet's original surface. Computer simulations reveal the elegant choreography hidden within this apparent chaos, showing how conservation of angular momentum and energy determine the fate of every particle of matter involved in the collision. Roughly 80% of both planets' mass remains gravitationally bound to form the proto-Earth, a molten sphere half again as large as the modern planet and spinning through its day in less than 5 hours. The remaining 20% of the original material escapes into a disc-shaped cloud of debris that extends from just above the proto-Earth surface to distances greater than the modern Moon's orbit. This circumterrestrial disk represents one of the most remarkable structures in the solar system's history, a temporary ring system containing more mass than all the terrestrial planets combined. The inner portions of the disk consist of rock vapor heated to thousands of degrees, while the outer regions harbor solid fragments ranging in size from dust grains to bodies hundreds of kilometers in diameter. Gravity and angular momentum sort this material according to size and orbital velocity, with the heaviest fragments settling into circular orbits close to the proto-Earth and the lightest particles spreading outward into eccentric ellipses that extend deep into space. The disk cools with a surprising rapidity, radiating its thermal energy into the vacuum of space at rates determined by the surface area of countless individual particles. Within decades, much of the vaporized rock condenses back into molten droplets that solidify into the spherical beads found today in lunar highland samples. These tiny glass spheres preserve within their crystal structure a record of the temperatures and pressures existing in Earth orbit during the immediate aftermath of the giant impact, providing modern scientists with direct evidence of the processes that shaped the early Earth-Moon system. Gravitational instabilities within the cooling disk begin almost immediately to concentrate material into ever larger aggregations. The physics governing this process mirrors the formation of planets from the solar nebula, but accelerated dramatically by the higher densities and velocities characteristic of impact-generated debris. Computer models show that most of the disk's mass coalesces into a single large body within 1,000 years, the gravitational attractor that will become Luna, Earth's primary satellite for the next 4 billion years. Yet the simulations also reveal something unexpected: a substantial fraction of Thea's iron-rich core, perhaps 10% of the impactor's total mass, survives the collision as a coherent body and settles into a stable orbit beyond the main accretion zone. This secondary satellite, roughly 1/10 the mass of the future Luna, follows its larger companion through the debris-strewn space around the proto-Earth like a cosmic afterthought, apparently destined for a brief and unremarkable existence as a minor moon. The gravitational interactions between these three bodies create a complex dynamical system that will evolve over millions of years according to the inexorable mathematics of celestial mechanics. The proto-Earth, still largely molten from the energy of impact and subsequent accretion, experiences massive tides raised by both satellites. These tidal forces dissipate orbital energy through friction in the molten rock, causing both moons to spiral gradually outward while simultaneously slowing the planet's rotation from its post-impact period of 5 hours toward the 24-hour day familiar to future life. Luna emerges from the debris disk as a fully molten world, its surface temperature maintained above the melting point of basalt by the heat generated during its rapid accretion and the tidal forces exerted by its proximity to Earth. The large satellite's internal structure differs dramatically from that of Earth or the other terrestrial planets, lacking the substantial iron core that characterizes worlds formed through the slow accumulation of primitive solar system materials. Instead, Luna consists primarily of silicate minerals similar to those found in Earth's mantle, supporting the theory that both worlds form from the same reservoir of materials blasted into space by the giant impact. The smaller satellite displays even more unusual characteristics, its composition reflecting its origin in the iron-rich core of the impactor Thea. Spectroscopic analysis of this secondary moon, if instruments existed to perform such measurements, would reveal mineralogies rich in metallic iron and nickel, quite different from the silicate-dominated composition of Luna or the proto-Earth. This chemical fingerprint will eventually provide crucial evidence for understanding the giant impact process, though the satellite itself will not survive long enough for direct examination by future spacecraft. The proto-Earth itself undergoes dramatic changes during the millennia following the impact, its surface gradually cooling as the heat generated by the collision radiates away into space. Yet, complete solidification of the planetary surface remains impossible while both satellites continue to raise massive tides in the molten rock, pumping energy into the interior through tidal friction and maintaining temperatures well above the melting point of most silicate minerals. Volcanic activity during this epoch dwarfs anything recorded in later geological history, with continent-sized calderas opening and closing across the planet's surface as convection currents in the magma ocean drive material circulation on truly planetary scales. The atmospheres surrounding all three worlds thicken dramatically during this period, fed by the constant outgassing from unprecedented levels of volcanic activity and the sublimation of volatile materials from the cooling debris disk. Water vapor, carbon dioxide, and sulfur compounds create dense atmospheric blankets that trap thermal radiation and maintain surface temperatures hundreds of degrees above what radiative cooling alone would permit. These early atmospheres glow with their own thermal radiation, visible across interplanetary distances as the Earth-Moon system slowly emerges from the cosmic violence of its birth. Lightning storms of unimaginable intensity rage through these thick atmospheres, triggered by the rapid circulation of electrically charged particles in the strong convection currents generated by extreme temperature gradients. The electromagnetic pulses from these atmospheric discharges reach far into space, creating radio noise that would overwhelm any sensitive receivers operating in the inner solar system. Aurora displays extend from pole to pole on all three worlds, as charged particles from the solar wind interact with their chaotic magnetic fields, painting the skies in colors that span the entire visible spectrum. The young sun continues to burn with reduced luminosity during this epoch, providing about 75% of the energy output that will characterize the star during Earth's later geological periods. Yet the greenhouse effect created by the thick atmospheric blankets more than compensates for this reduced stellar input, ensuring that all three worlds maintain surface temperatures well above the freezing point of water. No ice exists anywhere in the inner solar system during this time. All water remaining in vapor form in the dense atmospheres or dissolved in the magma oceans that cover the surfaces of the proto-Earth and its satellites. Solar wind during this period proves particularly intense, as the young sun has not yet developed the stable magnetic field structure that will eventually moderate its output of charged particles. This energetic solar wind strips away portions of the atmosphere surrounding all three worlds, particularly the lighter elements like hydrogen and helium that possess insufficient mass to remain gravitationally bound under the constant bombardment of high-energy particles. The atmospheric loss rates during this epoch exceed anything experienced by the terrestrial planets in later solar system history, requiring constant replenishment through volcanic outgassing to maintain the thick envelopes of gas that shroud the cooling worlds. As the first 1,000 years after impact draw to a close, the Earth-Moon system begins to assume characteristics recognizable to modern astronomers. Though still far from the stable configuration that will persist for billions of years, Luna has consolidated most of the debris disk into a single coherent body, while the smaller satellite maintains its distant orbit beyond the primary moon's gravitational influence. The proto-Earth continues to cool and contract, its surface beginning to show the first signs of crustal formation in regions where tidal forces prove insufficient to maintain complete melting. Yet the story of this early dual satellite system has barely begun, for gravitational mechanics operates with patience measured in millions rather than thousands of years. The complex three-body dance between Earth and its two moons will continue to evolve, driven by tidal forces and orbital resonances toward an inevitable conclusion that will reshape Luna itself and leave only one satellite to illuminate Earth's nights for the remainder of geological time. 10,000 years pass in the gradual cooling of worlds, and the Earth-Moon system settles into a rhythm that will persist for millions of years. The proto-Earth completes its contraction from the bloated, molten sphere created by the giant impact, its surface temperature dropping below the melting point of basalt for the first time since Thea's collision scattered both worlds across the inner solar system. Thin crusts of solid rock begin to form in regions where tidal heating proves insufficient to maintain complete melting, only to crack and reform as the planet's two satellites continue their gravitational dance overhead. Luna orbits at a distance of roughly 60,000 kilometers from Earth's surface, 10 times closer than the moon's modern position, completing one revolution every 7 hours while raising tides in the cooling magma ocean that reach heights measured in kilometers rather than meters. The massive satellite appears 15 times larger in Earth's sky than the moon familiar to future observers. A glowing orange disk that dominates the heavens and casts shadows sharp enough to read by during the long nights that still last only 2.5 hours. Beyond Luna's orbit, at a distance of nearly 200,000 kilometers, the smaller satellite follows its own elliptical path around the Earth-Moon system's common center of mass. This secondary moon, roughly 400 kilometers in diameter and composed primarily of the metallic iron and nickel that once formed Theia's core. Completes one orbit every 40 days. Its period locked in a complex resonance with Luna's motion that ensures the two satellites never approach closer than 50,000 kilometers to each other. Astronomers studying the dynamics of multiple satellite systems discover that such configurations represent a delicate balance between competing gravitational forces, stable only within narrow ranges of mass ratios and orbital distances. Computer simulations reveal that the Earth-Moon satellite system occupies a region of phase space where small perturbations can trigger dramatic instabilities, leading either to the ejection of one satellite into solar orbit or to eventual collision between the two moons. The mathematics governing three-body gravitational systems admits no general solution, making long-term predictions impossible without detailed numerical integration. The smaller satellite's highly elliptical orbit carries it as close as 100,000 kilometers to Earth during perigee and as far as 300,000 kilometers during apogee, a variation that subjects the tiny world to tremendous tidal stresses as it swings through its 40-day cycle. These stresses gradually heat the satellite's interior through tidal friction, maintaining its core in a molten state despite its small size and distance from the Sun. Volcanic activity on the secondary moon creates plumes of metallic vapor that escape the weak gravitational field and disperse into space, gradually reducing the satellite's mass and altering its orbital characteristics. The Earth itself undergoes profound changes during this epoch, as its rotation continues to slow under the combined tidal influence of both satellites. The planet's day lengthens from the 5-hour period immediately after impact to nearly 8 hours 10,000 years later, still far shorter than the 24-hour cycle that will eventually characterize terrestrial time, but approaching the point where atmospheric circulation can begin to establish stable patterns. The rapid rotation generates powerful Coriolis forces that drive atmospheric winds to velocities exceeding those of modern hurricanes, creating global circulation patterns unlike anything experienced in later geological history. These intense winds sculpt the cooling surface of the proto-Earth, carving valleys and ridges in the thin, basaltic crust that forms during brief periods when tidal heating subsides below the threshold required to maintain complete melting. Most of these early geological features prove ephemeral, erased by subsequent volcanic activity or tidal flexing, but some survive long enough to influence the patterns of crustal formation that will eventually stabilize into Earth's first permanent continents. The atmosphere during this period consists primarily of water vapor and carbon dioxide outgassed from the cooling magma ocean, with substantial quantities of sulfur compounds that give the sky a distinctive orange coloration, visible in the thermal glow emitted by the thick gas envelope. Atmospheric pressure at the surface reaches levels 10 times greater than modern Earth's atmosphere can sustain, creating a greenhouse effect so intense that surface temperatures remain above the boiling point of water, despite the gradual cooling of the underlying rock. Lightning storms rage continuously through this dense atmosphere, triggered by the extreme temperature gradients between the superheated surface and the cold vacuum of space above the atmospheric envelope. The electromagnetic pulses generated by these storms create radio interference detectable across the inner solar system, a constant crackling static that would overwhelm any communication systems operating during this epoch. The electrical activity also drives complex atmospheric chemistry, breaking apart water molecules and carbon dioxide to create exotic compounds that exist only under conditions of extreme temperature and pressure. Luna experiences its own dramatic geological evolution during this period, its surface remaining entirely molten under the intense tidal heating generated by its proximity to Earth. The large satellite's lack of a substantial iron core results in unusual magnetic field characteristics, with multiple poles and frequent reversals as circulation patterns in the molten silicate mantle create complex dynamo effects. These magnetic anomalies will eventually leave their signatures in the lunar rocks that cool and solidify over the coming millions of years, providing future scientists with evidence of the moon's early geological activity. The secondary satellite develops even more unusual characteristics during this epoch, Its metallic composition and elliptical orbit combining to create geological processes unknown elsewhere in the solar system. The extreme tidal stresses experienced during each close approach to Earth generate massive volcanic eruptions that spew molten iron and nickel into space at velocities approaching escape velocity. Some of this material falls back to the satellite's surface, creating impact craters filled with solidified metal rather than the rocky materials found on other worlds. Gravitational interactions between the two satellites create subtle but persistent perturbations in their orbital elements, causing Luna's orbit to slowly expand while the secondary satellite's path becomes increasingly eccentric. These changes occur with glacial slowness, requiring sensitive instruments and decades of observation to detect. But they represent the inexorable operation of celestial mechanics working to destabilize the delicate three-body system. The mathematics predicting this evolution admits no possibility of permanent stability. Only the question of whether the final outcome will occur in thousands, millions, or tens of millions of years. Solar wind during this epoch proves particularly destructive to the thick atmospheres surrounding all three worlds. As the young sun has not yet developed the stable magnetic field configuration that will eventually moderate its output of charged particles. The intense particle bombardment strips away atmospheric gases at rates that would completely erode modern planetary atmospheres within a few million years, requiring constant replenishment through volcanic outgassing to maintain the dense envelopes that shroud the cooling surfaces. The Earth's magnetic field remains chaotic and unstable during this period, generated by convection currents in the molten iron core but frequently reversing polarity or disappearing entirely for periods of centuries or millennia. During these episodes of magnetic weakness, solar wind particles penetrate directly to the upper atmosphere, creating aurora displays that extend from pole to pole and driving atmospheric escape rates even higher than normal. The planet's magnetic poles wander unpredictably across the surface, sometimes moving hundreds of kilometers per year as the dynamo mechanism struggles to establish coherent circulation patterns in the core. Evidence for this early magnetic instability survives in the magnetization patterns preserved in some of the oldest terrestrial rocks. Though most geological formations from this epoch have long since been destroyed by later tectonic activity or erosion, the few remaining samples show magnetic orientations that change frequently and dramatically, recording the chaotic field reversals characteristic of planetary dynamos in their earliest stages of development. These paleomagnetic signatures provide some of the only direct evidence for the conditions existing on Earth during the first few million years after the giant impact. As the first 100,000 years after Luna's formation draw to a close, the Earth-Moon system begins to develop the basic characteristics that will define its evolution for millions of years to come. Tidal forces continue to drive the gradual expansion of both satellites' orbits, while simultaneously slowing Earth's rotation toward more reasonable periods. The planet's surface cools sufficiently to support the first permanent crustal formations, though these early continents bear no resemblance to the stable landmasses that will eventually emerge from the geological processes of plate tectonics. Yet the fundamental instability of the three-body system ensures that this apparent tranquility cannot persist indefinitely. Hidden within the elegant mathematical relationships governing orbital mechanics lies the certainty that one satellite must eventually be lost, either ejected into independent solar orbit or drawn into collision with its companion. The question facing the Earth-Moon system as it enters its second 100,000 years concerns not whether this disruption will occur, but precisely when and how the final chapter of the dual satellite epoch will unfold. 100,000 years flow past like a geological exhale, and the gravitational choreography governing the Earth-Moon system reveals its underlying mathematical complexity. The three bodies move through space according to equations that possess no closed-form solution, their future trajectories determined only through the patient accumulation of countless small perturbations that gradually alter orbital elements with each passing revolution. Luna continues its slow spiral outward from Earth, while the smaller satellite follows an increasingly eccentric path that carries it alternately closer to and farther from the planet's gravitational embrace. The dance between the two moons develops subtle resonances that lock their orbital periods into precise mathematical relationships. Each satellite's motion influencing the other through gravitational forces that operate across hundreds of thousands of kilometers of empty space. Luna's period increases from 7 hours to nearly 11 hours as tidal friction dissipates its orbital energy and drives it away from Earth, while the secondary satellite's 40-day orbit becomes stretched into an elongated ellipse that brings it as close as 80,000 kilometers during perigee and carries it beyond 400,000 kilometers at apogee. These orbital resonances create predictable patterns in the tidal forces experienced by all three worlds, generating cycles of geological activity that repeat with clockwork precision over timescales measured in thousands of years. During periods when the satellites align on the same side of Earth, their combined gravitational pull raises tides in the planet's still molten interior that exceed anything experienced during the chaotic aftermath of the giant impact. Conversely, when the two moons occupy opposite sides of their orbits, tidal heating drops to minimum levels that allow portions of Earth's surface to cool below the melting point of basalt for extended periods. Computer simulations running these orbital integrations forward through millions of years reveal the existence of windows of instability embedded within the apparently stable three-body configuration. Small perturbations from solar gravitational effects, or from the gravitational influence of Venus and Mars during close planetary approaches, can trigger cascading changes in orbital elements that eventually destabilize the entire system. The mathematics governing these instabilities shows that the current configuration cannot persist indefinitely. Though the timescales involved range from hundreds of thousands to tens of millions of years, the secondary satellite proves particularly vulnerable to these destabilizing influences due to its highly eccentric orbit and relatively small mass compared to Luna. During close approaches to Earth, the tiny moon experiences tidal forces strong enough to deform its shape significantly, stretching the metallic body along the Earth satellite line and raising molten iron tides that reach heights of several kilometers above the mean surface. These extreme tidal stresses generate internal heating that maintains the satellite's core in a liquid state despite its small size and distance from the Sun. Volcanic activity on the secondary satellite creates spectacular displays visible from Earth during the closest approaches. When metallic magma fountains erupt with sufficient velocity to escape the weak gravitational field and form temporary clouds of vaporized iron and nickel that glow with their own thermal radiation. Some of this material falls back to the satellite's surface after cooling and condensing in the vacuum of space, creating impact craters filled with solidified metal droplets. Other portions of the volcanic debris achieve escape velocity entirely, dispersing into interplanetary space where they will eventually be swept up by other bodies or lost to the outer solar system. The Earth itself continues its gradual transformation from the molten world created by the giant impact towards something approaching a recognizable planet. Though the process remains far from complete, surface temperatures drop slowly as the atmosphere radiates thermal energy into space, but the greenhouse effect created by dense water vapor and carbon dioxide maintains conditions well above the boiling point of water. No liquid oceans can exist under these circumstances, though water vapor constitutes a major component of the thick atmospheric envelope that shrouds the cooling surface. Crustal formation proceeds in fits and starts, with thin basaltic plates solidifying during periods of reduced tidal heating, only to crack and remelt when the satellite's gravitational alignment drives fresh waves of magma to the surface. These early attempts at stable geology create a constantly changing patchwork of solid and molten regions that shifts location as the orbital dance overhead alters the patterns of tidal stress across the planet's surface. No permanent geological features survive this epoch, though the basic processes of crustal formation and destruction establish patterns that will eventually stabilize into plate tectonics. Luna undergoes its own remarkable evolution during this period, gradually developing the internal structure that will characterize the Moon for billions of years. The large satellite's initially molten interior begins to differentiate as heavier materials sink towards the center, and lighter components rise toward the surface, creating a small iron core surrounded by a thick mantle of olivine and pyroxene minerals. The cooling process generates massive volcanic eruptions that resurface entire hemispheres with basaltic lava flows, the precursors to the dark maria that will eventually become visible features of the lunar landscape. The tidal forces exerted by Earth's gravity create a permanent bulge in Luna's shape, elongating the satellite along the Earth-Moon line and establishing the synchronous rotation that will eventually lock one face of the Moon toward Earth for the remainder of solar system history. This tidal locking process occurs gradually over hundreds of thousands of years, with Luna's rotation period slowly increasing from its initial rapid spin towards synchronization with its orbital period around Earth. Magnetic field generation on Luna proves sporadic and weak due to the satellite's small iron core and slow rotation rate, creating only brief periods of coherent field structure separated by long intervals of magnetic chaos or complete field absence. During episodes when the lunar dynamo operates effectively, the satellite develops magnetic poles that wander across its surface in complex patterns determined by convection currents in the small molten core. These magnetic variations will eventually leave their signatures in the lunar rocks that cool and solidify during this epoch, providing future scientists with evidence of the Moon's early geological activity. The secondary satellite experiences even more dramatic magnetic phenomena due to its metallic composition and highly elliptical orbit. The extreme tidal stresses generated during each close approach to Earth drive powerful convection currents through the molten iron core, creating intense but short-lived magnetic fields that reach strengths comparable to those found on much larger planets. These magnetic episodes occur with the same 40-day periodicity as the satellite's orbital period, generating cycles of electromagnetic activity that create radio signals detectable across the inner solar system. Solar-wind interaction with the Earth-Moon system becomes increasingly complex as both satellites develop their own magnetospheres during periods of active dynamo generation. The charged particles streaming outward from the Sun encounter a constantly changing pattern of magnetic obstacles as the moons move through their orbits, sometimes creating continuous magnetic barriers that deflect the solar wind far from Earth's atmosphere. Other times, leaving the planet completely exposed to the full intensity of particle bombardment from space. Atmospheric evolution on all three worlds reflects this variable shielding from solar wind erosion, with atmospheric loss rates fluctuating dramatically depending on the magnetic field configurations present during any given epoch. Earth's thick atmosphere proves most resilient to erosion due to the planet's strong gravitational field. But even the massive atmospheric envelope surrounding the cooling world shows signs of gradual depletion in lighter elements like hydrogen and helium that lack sufficient mass to remain permanently bound under intense particle bombardment. The chemical composition of Earth's atmosphere begins to evolve during this period, as volcanic outgassing introduces new species of molecules into the gas envelope surrounding the planet. Sulfur compounds from volcanic emissions react with water vapor to create sulfuric acid droplets that condense into clouds capable of reflecting substantial amounts of solar radiation back to space. These early clouds provide the first mechanism for moderating surface temperatures through increased planetary albedo, though their effect remains small compared to the overwhelming greenhouse warming generated by the dense water vapor and carbon dioxide. Lightning activity reaches unprecedented intensities during this epoch as the extreme temperature gradients between the superheated surface and the cold upper atmosphere drive violent convection currents through the dense gas envelope. The electrical discharges generate electromagnetic pulses powerful enough to disrupt any electronic systems operating within several planetary radii, while simultaneously driving complex atmospheric chemistry that breaks apart simple molecules and recombines them into exotic compounds stable only under conditions of extreme temperature and pressure. As the Earth-Moon system approaches its millionth year after formation, the basic architecture of the three-body configuration has stabilized into the pattern that will govern its evolution for millions of years to come. Yet, embedded within this apparent stability lies the mathematical certainty that the current arrangement cannot persist indefinitely. For the equations governing three-body gravitational systems admit no solutions that remain bounded for infinite time. The question facing the early Earth-Moon system concerns not whether the dual satellite configuration will eventually collapse, but precisely how and when the inevitable gravitational catastrophe will unfold. The slow accumulation of orbital perturbations begins to manifest itself in measurable changes to the satellite system as the first million years pass into the second. Tidal forces continue their patient work of energy dissipation, drawing Luna gradually outward while simultaneously increasing the eccentricity of the secondary satellite's orbit through complex gravitational resonances that operate across timescales too long for human comprehension. The mathematical precision governing these changes reflects the fundamental conservation laws that govern all motion in the universe. Energy and angular momentum redistributing themselves according to principles established during the first moments after the Big Bang. Luna reaches a distance of 100,000 kilometers from Earth's surface, doubling its original orbital radius and reducing its apparent size in the sky to only 7 times that of the modern Moon. The massive satellite's orbital period extends to 18 hours, nearly matching Earth's rotational period as tidal locking gradually synchronizes the planet-Moon system. Surface temperatures on Earth drop below 1,000 degrees Celsius for the first time since the giant impact, allowing the formation of stable basaltic crusts that persist for thousands of years before renewed tidal heating cracks them apart and returns their material to the global magma ocean. The secondary satellite's orbit becomes increasingly elliptical as gravitational perturbations from Luna and the distant planets slowly pump energy into its eccentric motion. Perigee approaches within 60,000 kilometers of Earth's surface during the closest encounters, subjecting the small metallic world to tidal forces strong enough to visibly deform its shape from spherical to elongated. Apogee extends beyond 500,000 kilometers, carrying the satellite into regions of space where Earth's gravitational influence competes with that of the Sun and the other planets for control of its motion. These extreme orbital variations create cycles of geological activity on the secondary satellite that repeat with mathematical precision every 43 days. The satellite's orbital period having increased slightly due to tidal friction with Earth's gravitational field. During close approaches, massive eruptions of molten iron create temporary atmospheres of metallic vapor that glow with their own thermal radiation and remain visible from Earth for several days after each perigee passage. During distant phases of the orbit, the satellite cools rapidly in the vacuum of space, its surface temperature dropping to levels where even iron can solidify into permanent crustal formations. Computer models tracking the long-term evolution of this three-body system reveal the existence of chaotic zones embedded within the apparently regular orbital motion. Regions of phase space where small changes in initial conditions lead to dramatically different outcomes over geological time. The secondary satellite's trajectory passes through several of these chaotic zones during each orbital revolution, accumulating tiny perturbations that slowly but inexorably alter its path through space according to the strange attractors that govern non-linear dynamical systems. Earth's geological evolution accelerates as surface temperatures finally drop below the critical threshold that allows water vapor to condense into liquid droplets. The first primitive oceans form in low-lying regions where crustal cooling has proceeded far enough to create stable basins. Though these early seas remain extremely hot and acidic, more resembling the hydrothermal environments found around deep-sea volcanic vents than the blue oceans that will eventually cover most of the planet's surface. Steam rises continuously from these primitive seas, maintaining the thick atmospheric envelope that still shrouds the cooling world. The formation of liquid water represents a crucial milestone in Earth's evolution toward habitability, providing a medium where complex chemistry can begin the slow process of molecular evolution that will eventually lead to the emergence of life. Yet the extreme conditions present during this epoch, temperatures approaching the boiling point of water, intense ultraviolet radiation from the unshielded sun, and constant bombardment by meteorites and volcanic debris ensure that any chemical evolution remains limited to the most basic molecular processes. Luna continues its own dramatic geological transformation as its initially molten interior slowly cools and differentiates into the layered structure that will characterize the Moon for billions of years. A small iron core forms at the satellite's center, surrounded by a thick mantle of dense silicate minerals and capped by a thin crust of lighter materials that solidify as they rise toward the surface. Massive volcanic eruptions during this differentiation process create the dark basaltic plains that will eventually become known as the lunar Maria. Though the ongoing tidal heating from Earth ensures that much of the surface remains molten, the tidal forces raised by Earth's gravity begin to establish the synchronous rotation that will eventually lock one face of Luna permanently toward the planet. Though the process occurs gradually over hundreds of thousands of years, during this transitional period, different hemispheres of the lunar surface experience varying amounts of tidal heating, creating a complex pattern of geological activity that leaves permanent scars in the satellite's crustal structure. The hemisphere facing Earth undergoes more intense tidal flexing and remains molten longer, while the far side cools more rapidly and begins to develop the heavily cratered highland terrain that will become its most distinctive feature. Magnetic field generation on Luna proves weak and intermittent due to the satellite's small core and slow rotation rate, creating only brief episodes of coherent magnetic structure separated by long periods of field absence or chaotic behavior. During intervals when the lunar dynamo operates effectively, the weak magnetic field provides some protection from solar wind erosion, but proves insufficient to prevent the gradual loss of any atmosphere that might accumulate from volcanic outgassing. The airless environment that will characterize the Moon for most of its history begins to establish itself during this epoch. The secondary satellite develops its own unique geological characteristics as the extreme tidal stresses from its elliptical orbit drive processes unknown elsewhere in the solar system. The metallic composition of this small world allows tidal heating to propagate through its interior with unusual efficiency, maintaining global volcanic activity despite the satellite's tiny size and distance from the Sun. Eruptions of molten iron and nickel create surface features resembling terrestrial volcanoes, but composed entirely of metallic materials, rather than the silicate rocks found on other worlds. Solar activity during this epoch remains highly variable as the young Sun continues to evolve toward the stable main sequence star that will eventually provide steady illumination for the inner planets. Massive solar flares and coronal mass ejections bombard the Earth-Moon system with charged particles and electromagnetic radiation orders of magnitude more intense than anything experienced in later solar system history. These solar storms strip away portions of Earth's atmosphere while simultaneously driving the complex atmospheric chemistry that breaks apart water molecules and creates the first traces of free oxygen in the planetary environment. The interaction between solar wind and the Earth-Moon system's magnetic fields creates spectacular aurora displays that extend from pole to pole on all three worlds whenever magnetic field generation occurs. These early aurora reach intensities that would damage biological tissues if any life existed to observe them, painting the skies in colors that span the entire electromagnetic spectrum from radio waves to X-rays. The electromagnetic phenomena associated with these displays generate radio signals detectable across interplanetary distances, creating a constant background of noise that would interfere with any communication systems operating during this period. Atmospheric evolution on Earth begins to show the first signs of the complex chemistry that will eventually lead to the oxygen-rich environment capable of supporting complex life. Volcanic outgassing continues to supply water vapor, carbon dioxide, and sulfur compounds to the thick atmospheric envelope, while solar ultraviolet radiation drives photochemical reactions that break apart these simple molecules and recombine them into more complex species. Trace amounts of hydrogen peroxide, ozone, and other oxidizing compounds begin to appear in the upper atmosphere. The first hints of the great oxygenation event that will transform Earth's environment billions of years in the future. The gravitational perturbations affecting the secondary satellite's orbit gradually increase in amplitude as the small world passes through successive chaotic zones in its trajectory around Earth. Computer simulations reveal that these accumulated perturbations will eventually drive the satellite's orbit to even greater eccentricity, bringing it closer to Earth during perigee while simultaneously extending its apogee to distances where other gravitational influences become significant. The mathematical analysis of this orbital evolution shows that the current three-body configuration approaches a critical transition point where small changes can trigger dramatic instabilities. Evidence for the early bombardment period survives in the heavily cratered surfaces of both Luna and the secondary satellite, where impacts from asteroids and comets have created geological records that will persist for billions of years. The cratering patterns reveal bombardment rates thousands of times higher than those characterizing the modern solar system, reflecting the final cleanup of debris left over from planetary formation. Earth experiences similar bombardment during this epoch, but the planet's ongoing geological activity ensures that most impact craters disappear within millions of years through volcanic resurfacing or erosion. As the Earth-Moon system approaches its second million years of existence, the basic dynamics governing the three-body configuration have evolved toward the critical instabilities that will eventually reshape the entire satellite architecture. The mathematical inevitability of this evolution reflects the fundamental properties of gravitational systems operating under the constraints of energy and angular momentum conservation, principles that admit no permanent solutions for systems containing more than two gravitationally interacting bodies. The inexorable mathematics of orbital mechanics begins to assert itself more dramatically as the Earth-Moon system enters its third million years of existence. The secondary satellite's increasingly eccentric orbit carries it through gravitational resonances that amplify small perturbations into measurable changes in orbital elements. Each passage through perigee and apogee adding to the accumulated departures from its original circular path. Computer simulations tracking these orbital integrations reveal that the satellite has crossed the first critical threshold in the hierarchy of instabilities that govern three-body systems, entering a regime where its future trajectory becomes increasingly sensitive to external perturbations. Luna's outward migration continues with mathematical precision, the satellite reaching a distance of 150,000 kilometers from Earth's surface as tidal friction steadily dissipates orbital energy and transfers angular momentum from the planet's rotation to the Moon's revolution. The massive satellite's orbital period extends to 28 hours, approaching synchronization with Earth's lengthening day as the tidal locking process gradually slows the planet's rotation from its post-impact period of 5 hours towards something resembling a reasonable day-night cycle. The gravitational interaction between the two satellites creates complex patterns of orbital resonance that lock their periods into precise mathematical relationships, each moon's motion influencing the other through forces that operate across hundreds of thousands of kilometers of empty space. These resonances prove both stabilizing and destabilizing, maintaining the overall architecture of the three-body system while simultaneously pumping energy into the secondary satellite's increasingly eccentric orbit through a process that celestial mechanicians call the Kozai mechanism. The Kozai mechanism represents one of the most elegant and destructive phenomena in orbital dynamics, occurring when a third body's gravitational influence causes the eccentricity and inclination of an orbit to oscillate in coupled cycles that can drive satellites to extreme orbital configurations. In the Earth-Moon system, Luna's substantial gravitational field acts as the perturbing third body, gradually increasing the secondary satellite's orbital eccentricity while simultaneously tilting its orbital plane relative to the lunar orbit. These changes occur with glacial slowness, requiring hundreds of thousands of years to complete one full cycle, but their cumulative effect proves dramatic. The secondary satellite's perigee distance shrinks to 40,000 kilometers above Earth's surface during its closest approaches, subjecting the small metallic world to tidal forces that exceed anything experienced by natural satellites elsewhere in the solar system. The extreme gravitational gradient across the satellite's diameter creates differential acceleration between its Earth-facing and anti-Earth sides strong enough to visibly deform the body from its natural spherical shape into an elongated ellipsoid aligned with the local gravitational field. These tidal deformations generate massive internal heating through friction between different regions of the satellite's interior, moving at slightly different rates in response to Earth's gravitational pull. The metallic composition of the small world allows this tidal energy to propagate through its structure with unusual efficiency, maintaining its core in a molten state despite the satellite's tiny size and variable distance from the Sun. Volcanic activity during close approaches creates spectacular eruptions of liquid iron and nickel that achieve escape velocity and form temporary clouds of metallic vapor visible from Earth. Earth itself undergoes profound changes during this epoch as surface temperatures finally drop below the critical point where water vapor can condense into stable, liquid oceans. The first permanent seas form in the deepest basins created by early crustal formation. Though these primitive oceans bear little resemblance to the blue waters that will eventually cover most of the planet's surface, instead, they consist of extremely hot, acidic solutions laden with dissolved minerals leached from the cooling basaltic crust and volcanic gases absorbed from the still thick atmosphere. The formation of liquid oceans marks a crucial transition in Earth's evolution toward habitability, providing stable environments where complex chemistry can begin the molecular evolution that will eventually lead to life. Yet the extreme conditions characterizing these early seas, temperatures near the boiling point of water, pH levels comparable to battery acid, and constant bombardment by ultraviolet radiation from the unshielded sun ensure that any chemical evolution remains limited to the most basic processes of molecular self-organization. Luna's geological evolution accelerates as the satellite's internal differentiation approaches completion, creating the layered structure that will characterize the Moon for billions of years. The small iron core at the satellite's center generates a weak but coherent magnetic field during periods of active convection, providing sporadic protection from solar wind erosion while the lunar crust slowly thickens through the cooling and solidification of surface lava flows. Massive impact basins form during this period as large asteroids and comets continue to bombard the satellite's surface, creating the circular maria that will eventually become filled with dark basaltic lava. The tidal forces exerted by Earth's gravity complete the process of synchronous rotation that locks one hemisphere of Luna permanently toward the planet, establishing the familiar pattern where the same side of the Moon always faces Earth. This tidal locking creates a fundamental asymmetry in the satellite's geological evolution, with the Earth-facing hemisphere experiencing more intense tidal heating and prolonged volcanic activity while the far side cools more rapidly and develops the heavily cratered highland terrain that will become its most distinctive characteristic. Magnetic field generation throughout the Earth-Moon system remains chaotic and intermittent, as all three worlds struggle to establish stable dynamo processes in their molten cores. Earth's magnetic field shows the first signs of approaching the coherent dipole structure that will eventually shield the planet's atmosphere from solar wind erosion. Though frequent polarity reversals and episodes of field collapse continue to leave the world vulnerable to charged particle bombardment from space, during periods of magnetic weakness, aurora displays extend from pole to pole while atmospheric loss rates increase dramatically. The secondary satellite's extreme orbital eccentricity creates unique opportunities for scientific observation of tidal effects operating under conditions impossible to replicate elsewhere in the solar system. During close approaches to Earth, the small world experiences acceleration gradients that stretch and compress its metallic structure in ways that generate seismic waves detectable across interplanetary distances. These tidally driven earthquakes create patterns of surface fracturing that reflect the mathematical relationship between gravitational force and distance, providing a natural laboratory for studying the fundamental physics of tidal interactions. Solar activity during this epoch begins to moderate as the young sun approaches the stable configuration that will characterize its main sequence lifetime. Though solar wind intensity remains several times higher than levels typical of the modern solar system, massive coronal mass ejections continue to bombard the inner planets with charged particles and electromagnetic radiation. But the frequency and intensity of these events gradually decrease as the stellar magnetic field develops the complex structure that will eventually regulate solar output for billions of years. The chemical evolution of Earth's atmosphere shows the first clear evidence of processes that will eventually lead to the oxygen-rich environment capable of supporting complex life. Photochemical reactions driven by solar ultraviolet radiation begin to break apart water molecules in the upper atmosphere, creating trace amounts of free hydrogen and oxygen that represent the earliest signs of atmospheric chemistry dominated by something other than volcanic outgassing. The hydrogen escapes to space due to its low molecular weight, while the oxygen remains bound in various chemical compounds that slowly accumulate in the evolving atmospheric composition. Volcanic activity on all three worlds reaches unprecedented scales, as tidal heating and residual accretional energy drive geological processes that dwarf anything recorded in later solar system history. Earth experiences constant resurfacing through basaltic volcanism that creates and destroys crustal formations over timescales of thousands rather than millions of years. Luna undergoes massive volcanic eruptions that fill entire impact basins with molten rock, creating the dark plains that will eventually become known as the lunar Maria. The secondary satellite experiences eruptions of metallic magma that create surface features unique in the solar system. The gravitational perturbations affecting the secondary satellite's orbit continue to accumulate as the small world passes through successive orbital resonances with Luna and the distant planets. Mathematical analysis reveals that these perturbations follow a chaotic pattern that makes long-term prediction impossible beyond certain critical timescales. Though the overall trend toward increasing orbital eccentricity remains clear, computer simulations show that the satellite's trajectory will eventually carry it either into collision with Luna or into an escape orbit that ejects it from the Earth-Moon system entirely. As the Earth-Moon system approaches the end of its 3rd million years, the three-body configuration balances precariously between stability and chaos. With small perturbations capable of triggering dramatic changes in orbital architecture, the mathematical framework governing this evolution reflects the fundamental limitations of deterministic systems operating under the influence of multiple competing forces, where predictability gives way to chaos over sufficiently long timescales, and where the ultimate fate of the system depends on the precise timing of events that cannot be predicted in advance. The convergence begins subtly, hidden within the mathematical complexity of three-body gravitational dynamics. As the secondary satellite's orbit evolves through increasingly eccentric configurations that carry it both closer to Earth during perigee and farther away during apogee, 5 million years have passed since the giant impact created this delicate celestial arrangement, and the accumulated perturbations from Luna's gravitational influence have driven the small metallic world toward orbital parameters that exist at the very edge of dynamical stability. Computer simulations reveal that the satellite has entered what chaos theorists call a strange attractor, a region of phase space where tiny changes in initial conditions can trigger vastly different evolutionary pathways. Luna itself has migrated outward to a distance of 200,000 kilometers from Earth's surface, reducing its apparent size in the sky to roughly 3 times that of the modern Moon while extending its orbital period to 45 hours. The massive satellite's gravitational influence continues to shape the Earth-Moon system's evolution through tidal forces that dissipate energy and transfer angular momentum according to the fundamental conservation laws that govern all motion in the universe. Yet, Luna's outward migration has also reduced its ability to stabilize the secondary satellite's orbit, creating the conditions necessary for the gravitational catastrophe that mathematical analysis shows must eventually occur. The secondary satellite's orbital eccentricity has increased to values approaching unity, transforming its original circular path into an extremely elongated ellipse that brings the small world within 20,000 kilometers of Earth's surface during perigee, while carrying it beyond 1 million kilometers during apogee. These extreme orbital variations subject the metallic satellite to tidal forces that would tear apart any body composed of ordinary rock. Though the high tensile strength of iron and nickel allows the small world to maintain its structural integrity despite deformations that visibly alter its shape with each orbital revolution. During close approaches to Earth, the secondary satellite experiences acceleration gradients strong enough to generate seismic waves that propagate through its metallic structure at velocities approaching the speed of sound in iron. These tidally driven earthquakes create complex patterns of surface fracturing that reflect the mathematical relationship between gravitational force and distance, while simultaneously pumping enormous amounts of thermal energy into the satellite's interior through the mechanical work of repeatedly deforming and releasing its crystalline lattice structure. The extreme tidal heating maintains the satellite's core in a molten state, despite its small size and variable distance from the Sun, driving volcanic activity that creates eruptions of liquid metal unprecedented elsewhere in the solar system. During peak heating episodes that coincide with perigee passage, fountains of molten iron and nickel achieve escape velocity and form temporary atmospheres of metallic vapor that glow with thermal radiation detectable across interplanetary distances. Some of this material falls back to the satellite's surface after cooling in the vacuum of space, while other portions escape entirely to join the growing cloud of debris that surrounds the Earth-Moon system. Earth continues its gradual transformation toward recognizable planetary characteristics as surface temperatures stabilize below the boiling point of water, and the first permanent oceans establish themselves in low-lying regions between emergent crustal formations. These primitive seas remain extremely hot and chemically hostile, more resembling the hydrothermal environments found around deep-sea volcanic vents than the blue oceans that will eventually support complex life. Yet their existence marks a crucial milestone in the planet's evolution toward habitability, providing stable liquid environments where complex chemistry can begin the molecular evolution that will eventually lead to biological systems. The atmospheric composition shows the first clear evidence of chemical processes operating independently of volcanic outgassing as photochemical reactions driven by solar ultraviolet radiation begin to modify the mixture of water vapor, carbon dioxide, and sulfur compounds that characterizes the early terrestrial environment. Trace amounts of oxygen appear in the upper atmosphere as water molecules dissociate under intense radiation. Though this oxygen remains chemically bound in various compounds rather than existing as the free molecular oxygen that will eventually accumulate through biological processes. Luna's geological evolution approaches a critical transition as the satellite's internal differentiation nears completion, and its surface begins to develop the familiar dichotomy between heavily cratered highlands and smooth volcanic plains that will characterize the Moon for billions of years. The Earth-facing hemisphere experiences prolonged volcanic activity due to enhanced tidal heating, with massive lava flows filling the large impact basins created by asteroid and comet bombardment during the final phases of planetary formation. The far side cools more rapidly and preserves a heavily cratered surface that records the intense bombardment characterizing the early solar system. The tidal forces exerted by Earth's gravity have completed the synchronous rotation that locks one hemisphere of Luna permanently toward the planet, creating the stable configuration where the same side of the Moon always faces Earth. This tidal locking establishes a fundamental asymmetry that will influence lunar geology for the remainder of solar system history. With the near side experiencing different thermal and stress environments than the far side due to the constant orientation relative to Earth's gravitational field and thermal radiation. Magnetic field generation throughout the Earth-Moon system continues to evolve as the molten cores of all three worlds develop increasingly coherent convection patterns that drive dynamo processes capable of producing stable magnetic fields. Earth's magnetic field begins to approach the dipole configuration that will eventually provide effective shielding from solar wind erosion, though occasional polarity reversals and episodes of field weakness continue to leave the planet vulnerable to charged particle bombardment from space during periods of high solar activity. The secondary satellite's extreme orbital eccentricity creates conditions for magnetic field generation, unlike those found anywhere else in the solar system. With the alternating tidal stresses driving convection currents through the molten metallic core that vary dramatically with orbital phase. During close approaches to Earth, the enhanced tidal heating drives vigorous convection that generates intense but short-lived magnetic fields, comparable in strength to those found on much larger planetary bodies. During distant phases of the orbit, reduced tidal input allows the magnetic field to decay to negligible levels before the next perigee passage restarts the cycle. The gravitational resonances linking the orbits of Luna and the secondary satellite begin to break down as the small world's increasing eccentricity carries it through orbital configurations that no longer maintain the precise period ratios required for stable resonant motion. This resonance breaking represents a crucial step in the evolutionary pathway toward orbital instability, removing one of the primary mechanisms that has maintained the three-body system's coherence for millions of years. Mathematical analysis shows that once these resonances disappear, the secondary satellite's orbital evolution will accelerate rapidly toward one of two possible outcomes: ejection from the Earth-Moon system or collision with Luna. Solar activity continues to moderate as the young sun approaches the stable main sequence configuration that will characterize its lifetime. Though solar wind intensity and variability remain significantly higher than levels typical of the modern solar system, the gradual decrease in solar activity allows Earth's atmosphere to retain volatile compounds more effectively, supporting the accumulation of water vapor and other gases that will eventually create the dense atmospheric envelope necessary for complex weather systems and climate regulation. The chemical evolution of Earth's oceans begins to show evidence of the complex molecular processes that will eventually lead to the emergence of life. Though the extreme conditions characterizing these early seas limit chemical evolution to the most basic forms of molecular self-organization, high temperatures, intense ultraviolet radiation, and constant bombardment by volcanic debris create environments that simultaneously promote and destroy complex molecular structures. Establishing a dynamic equilibrium between synthesis and decomposition that represents the earliest stage of chemical evolution on Earth. Computer simulations tracking the long-term evolution of the Earth-Moon system reveal that the current epoch represents a critical transition period where the accumulated effects of millions of years of orbital perturbations approach the threshold for triggering dramatic changes in the satellite architecture. The mathematical framework governing this evolution shows that the secondary satellite has entered a chaotic regime where its future trajectory becomes increasingly unpredictable. Though certain general outcomes remain statistically favored over others, as the Earth-Moon system enters its 6th million years of existence, the stage becomes set for the gravitational drama that will resolve the fundamental instability embedded within any three-body configuration. The precise timing of this resolution depends on the chaotic dynamics that govern the secondary satellite's motion, making exact prediction impossible while ensuring that some form of dramatic orbital evolution must occur within the relatively near future. The question facing the early Earth-Moon system concerns not whether this instability will manifest itself, but rather how and when the final chapter of the dual satellite epoch will unfold across the vast theater of space. The mathematics of orbital decay begins to accelerate as gravitational perturbations accumulate beyond the threshold where linear approximations remain valid, driving the secondary satellite's trajectory into the non-linear regime where small causes produce disproportionately large effects. 10 million years have elapsed since the giant impact scattered debris across the inner solar system, and the complex three-body dance between Earth, Luna, and the small metallic satellite approaches its inevitable conclusion through processes that operate with the mathematical certainty of a geometric proof unfolding across geological time. The secondary satellite's orbital eccentricity has increased to extreme values that carry it within 15,000 kilometers of Earth's surface during perigee, while extending its apogee beyond 2 million kilometers, creating an orbital configuration so elongated that the small world spends most of its time in the distant reaches of the Earth-Moon system's gravitational influence. Yet it is during the brief periods of close approach that the most dramatic changes occur. As tidal forces strong enough to liquefy solid rock pump enormous amounts of energy into the satellite's interior and drive geological processes unlike anything found elsewhere in the solar system, Luna has continued its gradual outward migration to a distance of 300,000 kilometers from Earth, reducing its apparent size in the sky to roughly twice that of the modern Moon while extending its orbital period to 72 hours. The massive satellite's gravitational influence has weakened with distance, reducing its ability to maintain the orbital resonances that once stabilized the three-body system and allowing the secondary satellite's chaotic trajectory to evolve toward ever more extreme configurations. Computer simulations reveal that the current orbital architecture has entered a regime where catastrophic instability becomes not just possible but inevitable within the next few million years. The Kozai mechanism continues to drive the coupled evolution of the secondary satellite's eccentricity and orbital inclination, creating cycles of gravitational perturbation that repeat every few 100,000 years with gradually increasing amplitude. Each cycle carries the small world closer to Earth during perigee while simultaneously tilting its orbital plane farther from the lunar orbit, establishing the conditions necessary for a close encounter between the two satellites that will ultimately determine the fate of the dual moon system. During its closest approaches to Earth, the secondary satellite experiences tidal acceleration gradients that exceed the strength of chemical bonds in most materials, creating internal stresses that would shatter any body composed of ordinary silicate rock. Only the exceptional tensile strength of the metallic iron and nickel comprising the satellite's structure allows it to survive these extreme conditions. Though the constant flexing and deformation of its crystalline lattice generates seismic waves that propagate through the small world's interior at acoustic velocities approaching several kilometers per second. The extreme tidal heating driven by these close encounters maintains the satellite's entire interior in a molten state, despite its small size and variable distance from the Sun, creating a geological environment where liquid metal flows through fractures in the partially solidified crust like terrestrial lava flowing through volcanic fissures. Eruptions during perigee passages achieve escape velocities that launch molten iron droplets into ballistic trajectories, extending thousands of kilometers above the satellite's surface, creating temporary atmospheres of metallic vapor that glow with thermal radiation visible across the inner solar system. Earth's surface continues to cool toward temperatures compatible with complex chemistry, as the planet's thick atmosphere gradually radiates away the thermal energy inherited from the giant impact and ongoing volcanic activity. The first stable continental masses begin to emerge from the global magma ocean as lighter silicate materials differentiate toward the surface and solidify into primitive crustal formations that can withstand the reduced levels of tidal heating characterizing this epoch. These early continents remain small and unstable compared to the massive land masses that will eventually emerge through plate tectonic processes. But their existence marks a crucial milestone in Earth's geological evolution. The primitive oceans that have formed in low-lying regions between emergent crustal formations begin to show evidence of the complex chemistry that will eventually lead to the emergence of life. Though the extreme conditions characterizing these early seas continue to limit molecular evolution to the most basic processes of chemical self-organization, water temperatures approaching the boiling point drive rapid reaction rates that both promote and destroy complex molecular structures, creating a dynamic equilibrium between synthesis and decomposition that represents the earliest stage of prebiotic chemistry on Earth. Luna's geological evolution approaches completion as the satellite's internal differentiation establishes the layered structure that will characterize the Moon for billions of years. With a small iron core surrounded by a thick mantle of dense silicate minerals and capped by a thin crust of lighter materials that have solidified during the cooling process, the Earth-facing hemisphere continues to experience enhanced volcanic activity due to tidal heating. filling the large impact basins with dark basaltic lava flows that will eventually become known as the Lunar Maria. While the far side preserves the heavily cratered highland terrain that records the intense bombardment characterizing the early solar system, the gravitational interaction between Luna and the secondary satellite creates complex perturbations that gradually alter both objects' orbital elements through processes that operate too slowly to observe directly, but prove inexorable over geological time. The secondary satellite's increasingly eccentric orbit carries it through gravitational resonances with Luna that pump additional energy into its motion while simultaneously altering the large satellite's own trajectory in subtle but measurable ways. These mutual perturbations represent the final stage of three-body evolution before the system's fundamental instability manifests itself through catastrophic orbital changes. Magnetic field generation throughout the Earth-Moon system stabilizes as the molten cores of all three worlds develop coherent convection patterns capable of sustaining long-lived dynamo processes. Earth's magnetic field approaches the stable dipole configuration that will eventually provide effective protection from solar wind erosion, reducing atmospheric loss rates and allowing volatile compounds to accumulate in quantities sufficient to support complex atmospheric chemistry and eventually biological processes. The secondary satellite's extreme orbital variations continue to drive unique magnetic phenomena as alternating tidal stresses create convection currents in the molten metallic core that vary dramatically with orbital phase. Peak magnetic field strengths during close approaches to Earth reach levels comparable to those found on much larger planetary bodies, while minimum field strengths during distant orbital phases drop to negligible values before the next perigee passage restarts the electromagnetic cycle. Solar-wind interaction with the Earth-Moon system becomes increasingly complex as the planets develop stable magnetospheres that deflect charged particles away from their atmospheres while simultaneously creating wake structures that extend millions of kilometers downstream from each world. The secondary satellite's highly variable magnetic field creates a constantly changing pattern of obstacles to solar wind flow, sometimes reinforcing Earth's magnetic shielding and other times leaving the planet completely exposed to particle bombardment, depending on the relative positions of all three bodies. The chemical composition of Earth's atmosphere begins to evolve beyond the simple mixture of volcanic gases that characterize the immediate post-impact period as photochemical processes driven by solar radiation create increasingly complex molecular species through the breakdown and recombination of water vapor, carbon dioxide, and sulfur compounds. Trace amounts of hydrogen peroxide, methane, and other reactive molecules appear in the atmospheric inventory, representing the first steps toward the complex atmospheric chemistry that will eventually support biological activity. Computer simulations tracking the orbital evolution of the Earth-Moon system reveal that the secondary satellite's trajectory has entered the final phase of chaotic motion before catastrophic instability manifests itself through either collision with Luna or ejection from the system entirely. The mathematical analysis shows that both outcomes remain possible depending on the precise timing of gravitational perturbations from the outer planets and the detailed three-body dynamics that govern the satellite's motion through increasingly extreme orbital configurations. The gravitational resonances that once maintained the stability of the three-body system continue to weaken as the secondary satellite's orbital period becomes increasingly decoupled from Luna's motion, removing the last stabilizing influences that have prevented catastrophic evolution for millions of years. Once these resonances disappear entirely, the small satellite's orbital evolution will accelerate rapidly toward one of the two possible endpoints predicted by celestial mechanics: either a grazing collision with Luna that will reshape both bodies, or gravitational ejection into independent solar orbit. As the Earth-Moon system approaches its 10th million years of existence, the stage becomes fully set for the dramatic conclusion of the dual satellite epoch. The precise outcome remains unpredictable due to the chaotic nature of three-body gravitational systems. But the mathematical framework governing orbital evolution ensures that some form of major reconfiguration must occur within the next few million years. The question facing the early Earth-Moon system concerns not whether this transformation will take place, but rather which of the possible scenarios will unfold when the accumulated perturbations finally exceed the threshold for gravitational catastrophe. The final approach unfolds with a slow-motion inevitability of continental drift viewed across geological time. As 15 million years of accumulated gravitational perturbations drive the secondary satellite's orbit toward its ultimate intersection with Luna's path through space, computer simulations running forward through the complex mathematics of three-body dynamics reveal that the chaotic evolution of orbital elements has reached a critical threshold where small changes in the system's configuration can trigger dramatically different outcomes. Though all possible futures converge toward the same general conclusion, the dual satellite epoch draws toward its close through processes that operate with the mathematical certainty of physical law. The secondary satellite's trajectory has evolved into an extremely elongated ellipse that brings the small metallic world within 10,000 kilometers of Earth's surface during perigee while carrying it beyond 3 million kilometers during apogee, creating orbital variations so extreme that the satellite spends most of its time beyond Luna's orbit despite originating much closer to Earth. The gravitational perturbations from Luna's substantial mass have pumped the small world's orbital eccentricity to values approaching the theoretical maximum for bound orbits, establishing the conditions necessary for the close encounter that mathematical analysis shows must eventually occur. Luna itself has migrated outward to a distance of 400,000 kilometers from Earth, only slightly closer than the modern Moon's orbital radius, reducing its apparent size in the sky to roughly 1.5 times that familiar to future observers, while extending its orbital period to 120 hours. The massive satellite's gravitational influence continues to shape the Earth-Moon system's evolution through tidal forces that dissipate energy and redistribute angular momentum according to conservation laws. But the increasing distance has weakened Luna's ability to control the secondary satellite's chaotic motion through orbital resonances. The Kozai mechanism driving the coupled evolution of eccentricity and orbital inclination reaches its maximum amplitude as the secondary satellite's orbit becomes tilted nearly 40 degrees relative to Luna's equatorial plane, creating the geometric configuration necessary for a close encounter between the two worlds. The mathematical framework governing this evolution shows that the satellite's trajectory will eventually carry it across Luna's orbital path at a relative velocity of several kilometers per second. Though the precise timing and impact parameters remain sensitive to tiny perturbations that make exact prediction impossible beyond certain critical time horizons. During its closest approaches to Earth, the secondary satellite experiences tidal forces strong enough to overcome the structural integrity of most geological materials, creating internal stresses that generate continuous seismic activity throughout the small world's metallic interior. The extreme gravitational gradients across the satellite's diameter stretch and compress its crystalline structure in ways that pump enormous amounts of thermal energy into the molten core, maintaining temperatures sufficient to keep the entire interior in a liquid state despite the satellite's small size and variable distance from the Sun. The volcanic activity driven by these extreme tidal forces creates eruptions of molten iron and nickel that achieve escape velocities exceeding anything recorded elsewhere in the solar system, launching streams of liquid metal thousands of kilometers above the satellite's surface before the material cools and solidifies into spherical droplets that rain back down across the fractured landscape. Some of this metallic debris escapes the satellite's weak gravitational field entirely, forming a tenuous cloud of iron particles that spreads throughout the Earth-Moon system and will eventually be incorporated into both Luna's surface and Earth's early crustal formations. Earth continues its transformation toward planetary maturity as surface temperatures stabilize within ranges compatible with liquid water and complex chemistry, allowing the first permanent oceans to establish themselves across vast regions of the cooling surface. These primitive seas remain hot and chemically hostile compared to modern terrestrial environments, but their existence provides stable liquid media where molecular evolution can begin the gradual processes that will eventually lead to biological systems capable of self-replication and metabolic activity. The atmospheric composition evolves beyond the simple mixture of volcanic gases, characterizing the immediate post-impact period as photochemical reactions, driven by solar, ultraviolet radiation create increasingly complex molecular species through the systematic breakdown and recombination of water vapor, carbon dioxide, and sulfur compounds. Trace amounts of ammonia, methane, and hydrogen sulfide begin to appear in the atmospheric inventory, representing intermediate steps in the chemical evolution that will eventually produce the oxygen-rich environment capable of supporting complex life. Luna's geological activity begins to wane as the satellite's internal heat sources become depleted through radiative cooling and the reduced tidal heating associated with its increasing distance from Earth. The massive volcanic eruptions that filled the large impact basins with dark basaltic lava flows gradually subside, leaving the familiar pattern of smooth maria surrounded by heavily cratered highland terrain that will characterize the lunar surface for billions of years. The synchronous rotation established through tidal locking ensures that the same hemisphere always faces Earth, creating a permanent dichotomy between the near side and far side that influences geological processes through differential heating and gravitational effects. The gravitational perturbations affecting both satellites' orbits continue to accumulate as the secondary satellite's increasingly eccentric trajectory carries it through successive close encounters with Luna's gravitational field, each passage adding to the complex pattern of orbital evolution that governs the three-body system's ultimate fate. Computer simulations reveal that these perturbations follow a chaotic pattern that makes precise long-term prediction impossible. Though statistical analysis shows that collision between the two satellites becomes increasingly probable as their orbital paths intersect more frequently, magnetic field generation throughout the Earth-Moon system reaches a relatively stable configuration as the molten cores of all three worlds develop coherent convection patterns capable of sustaining long-lived dynamo processes. Earth's magnetic field assumes the dipole structure that will provide effective shielding from solar wind erosion for billions of years, while Luna's weaker field begins the gradual decay that will eventually leave the satellite magnetically inactive. The secondary satellite's extreme orbital variations continue to drive the most intense magnetic phenomena in the system, with field strengths during close approaches to Earth reaching levels that create measurable perturbations in the planet's own magnetosphere. The final orbital resonances linking the secondary satellite's motion to Luna's revolution around Earth begin to break down irreversibly as the small world's extreme eccentricity carries it through configurations that can no longer maintain the precise period ratios required for stable resonant behavior. This resonance breaking represents the last stabilizing influence preventing catastrophic orbital evolution, removing the final barrier to the gravitational encounter that mathematical analysis shows must occur within the next million years. Solar activity approaches the stable main sequence levels that will characterize the Sun's lifetime as the stellar magnetic field develops the complex structure necessary to regulate the output of charged particles and electromagnetic radiation. The gradual moderation of solar wind intensity allows Earth's atmosphere to retain volatile compounds more effectively while reducing the erosion rates that have stripped away substantial portions of the early atmospheric envelope during periods of high solar activity. The chemical evolution of Earth's primitive oceans accelerates as declining temperatures and stabilizing atmospheric composition create conditions more favorable to the formation and preservation of complex molecular structures. The first organic compounds begin to appear through abiotic synthesis processes driven by lightning, ultraviolet radiation, and hydrothermal activity. Though these early molecules remain far simpler than the complex biochemistry that will eventually emerge through biological evolution. Computer models tracking the detailed orbital mechanics of the Earth-Moon system show that the secondary satellite's trajectory has entered the final phase of chaotic evolution before collision with Luna becomes inevitable. The mathematical analysis reveals that both satellites will approach within a few thousand kilometers of each other during their next close encounter, creating tidal forces strong enough to disrupt both bodies and scatter debris throughout the Earth-Moon system. The precise outcome of this impending collision depends on the detailed impact parameters determined by the chaotic dynamics governing the secondary satellite's motion. But all scenarios converge toward the same general result: the transformation of the dual satellite system into a single large moon accompanied by a debris field of smaller fragments. The collision will release energy equivalent to billions of nuclear weapons, reshaping Luna's surface and creating the geological features that will remain visible for billions of years as testament to this ancient catastrophe. As the Earth-Moon system approaches the end of its 15th million years of existence, the gravitational drama that has unfolded across geological time reaches its climax through processes that operate according to the fundamental laws governing matter and energy in the universe. The dual satellite epoch that began with the violence of the giant impact will end with another collision, completing a cycle of creation and destruction that reflects the dynamic nature of planetary systems evolving under the influence of gravitational forces operating across vast expanses of space and time. The question no longer concerns whether this collision will occur, but rather how the impact will unfold and what new configuration will emerge from the debris of two worlds meeting in the darkness between Earth and the distant stars. The mathematical certainty of this outcome reflects the deep structure of physical law that governs all motion in the cosmos. From the smallest atomic interactions to the grandest choreography of galaxies spinning through the expanding universe, the collision unfolds across several hours of cosmic violence that reshapes both satellites and scatters debris throughout the Earth-Moon system, marking the end of the dual satellite epoch through processes that operate on scales vast enough to dwarf terrestrial experience, yet precise enough to follow the mathematical relationships governing the conservation of energy and momentum. 20 million years after the giant impact first created this delicate three-body configuration, gravitational mechanics completes the inexorable evolution that transforms two separate worlds into a single unified satellite accompanied by a cloud of smaller fragments destined to rain down across the lunar surface for millennia to come. The final approach begins when the secondary satellite's extremely eccentric orbit carries it within 50,000 kilometers of Luna's position, close enough for the gravitational fields of both bodies to begin distorting each other's shapes through tidal forces that stretch and compress the solid rock and liquid metal comprising their interiors. Computer simulations reveal that this encounter occurs at a relative velocity of nearly 3 kilometers per second, fast enough to ensure catastrophic disruption of both satellites but slow enough to prevent complete vaporization of their constituent materials. The smaller satellite, weakened by millions of years of extreme tidal flexing that has fractured its metallic structure into a complex network of stress-relieved segments, begins to break apart before physical contact occurs as Luna's gravitational field exerts differential forces across its diameter that exceed the tensile strength of iron and nickel crystals. The leading hemisphere fragments into a shower of metallic debris, ranging in size from mountain-sized boulders to microscopic dust particles, each fragment following its own ballistic trajectory according to the gravitational forces and initial velocities imparted by the disruption process. Luna experiences its own dramatic deformation as the approaching debris field creates a complex pattern of gravitational perturbations that raise tides in the satellite's partially molten interior, reaching heights of several kilometers above the mean surface level. The lunar crust, already weakened by billions of years of impact cratering and volcanic activity, cracks along pre-existing fault lines as these massive tidal bulges migrate across the satellite's surface in response to the rapidly changing gravitational field created by the fragmenting secondary satellite. The actual collision begins when the largest fragments of the disrupted secondary satellite strike Luna's surface at velocities sufficient to create impact craters hundreds of kilometers in diameter, each impact releasing energy equivalent to millions of nuclear weapons and excavating volumes of lunar material measured in thousands of cubic kilometers. The kinetic energy of these high-velocity impacts converts entirely into heat and pressure, creating fireballs that briefly achieve temperatures comparable to those found in stellar cores while generating shockwaves that propagate through Luna's interior at velocities exceeding the speed of sound in solid rock. The largest single fragment, roughly 100 kilometers in diameter and composed primarily of the secondary satellite's iron-nickel core, strikes Luna's far side near what will eventually become known as the South Pole Aitken Basin, creating the largest impact structure in the Earth-Moon system's history. The collision excavates a crater nearly 2,000 kilometers in diameter and 15 kilometers deep, removing enough material to expose Luna's deep interior structure while simultaneously depositing a layer of metallic debris across vast regions of the lunar surface. Smaller fragments continue to rain down across Luna's surface for hours after the initial impact, each collision adding to the complex pattern of crater formation that will characterize the satellite's far side for billions of years. The metallic composition of this debris creates impact structures quite different from those formed by the silicate asteroids and comets that typically bombard planetary surfaces, with higher densities and different mechanical properties that influence both the excavation process and the characteristics of the resulting craters. The energy released by this cosmic bombardment proves sufficient to remelt substantial portions of Luna's crust, creating vast lava flows that begin to fill the largest impact basins even as the cratering process continues around them. The far side of the satellite experiences the most intense bombardment due to the orbital geometry of the collision, while the Earth-facing hemisphere receives a lighter but still substantial rain of debris that creates thousands of smaller craters scattered across the lunar Maria and Highland regions. Earth witnesses this cosmic catastrophe as a brilliant display of thermal radiation visible across the entire night hemisphere as the impact-generated fireballs briefly outshine the combined luminosity of both satellites. The electromagnetic pulses created by the high-velocity impacts generate radio signals detectable across interplanetary distances, while the debris clouds thrown up by the largest collisions create temporary atmospheres around Luna that glow with their own thermal emission for days after each major impact. The gravitational effects of redistributing so much mass across Luna's surface create measurable perturbations in the satellite's orbital motion around Earth, slightly altering its period and eccentricity in ways that will influence tidal effects on the planet for millions of years to come. The addition of iron-rich material to Luna's predominantly silicate composition also affects the satellite's internal structure and magnetic field generation, creating regional magnetic anomalies that will persist long after the global magnetic field generated by the lunar core eventually decays to negligible levels. Computer simulations tracking the long-term evolution of the debris field reveal that most of the smaller fragments will eventually be swept up by Luna's gravitational field over the next few million years, gradually increasing the satellite's mass while simultaneously smoothing the most extreme topographical features created by the initial bombardment. Some material escapes the Earth-Moon system entirely, scattered into independent solar orbits by the violence of the collision process, while other fragments fall toward Earth to create a brief but intense meteor shower that adds metallic components to the planet's early crustal formations. The aftermath of the collision establishes Luna as the sole satellite of Earth for the remainder of solar system history, ending the dual moon epoch that began with the giant impact 20 million years earlier. The merged satellite displays characteristics inherited from both its predecessors: the predominantly silicate composition and large size derived from the original Luna, combined with the metallic enrichment and complex surface geology created by incorporating the disrupted secondary satellite. The far side of Luna develops the heavily cratered highland terrain that will become its most distinctive feature, preserving a record of the intense bombardment that accompanied the collision between the two satellites. The near side, partially shielded from the debris field by Luna's own bulk, retains more of the smooth volcanic plains that characterize the original satellite's Earth-facing hemisphere. Though even these regions show evidence of the cosmic catastrophe in the form of scattered impact craters and metallic debris deposits, Earth's geological evolution continues unaffected by the lunar collision. Though the planet experiences enhanced meteor activity for several thousand years as debris from the satellite merger gradually falls through the atmosphere to impact the cooling surface. The metallic composition of this material adds iron, nickel, and trace amounts of rare elements to Earth's crustal inventory, contributing to the chemical diversity that will eventually support complex geological processes and biological evolution. The atmospheric composition shows continued evolution toward greater chemical complexity as photochemical processes driven by solar radiation create increasingly sophisticated molecular species through the breakdown and recombination of volcanic gases and impact-delivered volatile compounds. The gradual accumulation of water vapor in the cooling atmosphere approaches the critical point where widespread condensation can begin to form the extensive cloud systems that will eventually regulate Earth's climate through the greenhouse effect and albedo feedback mechanisms. Luna's post-collision evolution proceeds through a phase of intense geological activity as the thermal energy deposited by the bombardment drives widespread volcanic eruptions that continue to reshape the satellite's surface for millions of years after the initial collision. The largest impact basins gradually fill with dark basaltic lava flows, creating the familiar pattern of lunar Maria that will remain visible from Earth for billions of years as testament to this ancient cosmic catastrophe. As the Earth-Moon system enters its third decade of existence, the fundamental architecture that will characterize it for the remainder of solar system history has finally stabilized through the violent processes of collision and merger that represent the natural conclusion of three-body gravitational systems. The single large satellite that emerges from this cosmic drama carries within its structure and surface geology the complete history of its formation. From the giant impact that created the original Earth-Moon system through the gradual orbital evolution and ultimate collision that transformed two separate worlds into one unified body, orbiting in the darkness beyond Earth's protective atmosphere. The debris settles across Luna's fractured landscape with the patience of geological process, each fragment following ballistic trajectories determined by the gravitational field of the newly unified satellite and the complex velocity vectors imparted during the collision that merged two separate worlds into one scarred but coherent body. Millions of metallic fragments ranging in size from house-sized boulders to microscopic dust particles continue to rain down across the lunar surface for decades after the initial impact, each subsequent collision adding to the complex cratering pattern that will characterize the Moon's far side for billions of years, while gradually redistributing the iron and nickel inherited from the disrupted secondary satellite. The largest impact basins created during the collision begin to cool and solidify as the thermal energy deposited by high-velocity impacts radiates away into the vacuum of space, leaving behind permanent scars in Luna's crust that expose the satellite's deep interior structure through crater walls and central peak formations that rise kilometers above the surrounding terrain. The South Pole Aitken Basin, excavated by the collision with the secondary satellite's primary fragment, creates a window into Luna's internal architecture that reveals the layered structure inherited from the satellite's formation in the debris disk surrounding the proto-Earth 20 million years earlier. Computer simulations tracking the orbital dynamics of the remaining debris field show that most of the smaller fragments will eventually be swept up by Luna's gravitational influence over the next few million years. Following complex trajectories that spiral inward from their initial ballistic paths to impact the satellite's surface at velocities determined by the Moon's escape velocity and the orbital mechanics governing their descent. This gradual accretion process will add roughly 1% to Luna's total mass while simultaneously smoothing the most extreme topographical features created by the initial bombardment. Earth continues to experience enhanced meteor activity as debris scattered by the lunar collision gradually falls through the planet's atmosphere, creating spectacular fireball displays visible across the night sky during peak bombardment periods that occur when the planet's orbit carries it through regions of space with higher concentrations of metallic fragments. Most of this material burns up completely during atmospheric entry due to the high velocities and small sizes characteristic of impact debris, though some larger fragments survive to reach the surface and contribute trace amounts of iron, nickel, and rare elements to Earth's evolving crustal composition. The unified Luna begins to develop the internal structure that will characterize the Moon for the remainder of solar system history as the thermal energy deposited by the collision drives differentiation processes that redistribute heavy and light elements according to their densities and chemical affinities. The metallic material inherited from the secondary satellite sinks toward Luna's center, slightly enlarging the small iron core that formed during the satellite's original accretion while creating regional variations in density and magnetic properties that will influence geological processes for millions of years. Volcanic activity on Luna reaches unprecedented levels as the heat generated by the collision melts substantial portions of the satellite's crust and upper mantle, driving massive eruptions that begin to fill the largest impact basins with dark basaltic lava flows. These volcanic episodes create the smooth plains that will eventually become known as the Lunar Maria. Though the ongoing bombardment by smaller debris fragments continues to crater these fresh lava surfaces even as they solidify, creating the complex overlapping relationships between impact and volcanic features that characterize much of the lunar landscape. The far side of Luna, which bore the brunt of the collision with the secondary satellite, develops the heavily cratered highland terrain that will become its most distinctive characteristic, preserving a detailed record of the intense bombardment that accompanied the merger of the two satellites. The asymmetric distribution of impact craters between the near and far sides establishes the fundamental dichotomy that will distinguish these two hemispheres for billions of years. With the Earth-facing side retaining more of the smooth volcanic features inherited from the original Luna's geological evolution, Earth's magnetic field begins to assume the stable dipole configuration that will provide effective shielding from solar wind erosion for the remainder of the planet's geological history. As convection currents in the molten iron core develop the coherent circulation patterns necessary to sustain long-lived dynamo processes, the establishment of a strong planetary magnetic field marks a crucial milestone in Earth's evolution toward habitability. Reducing atmospheric loss rates and allowing volatile compounds to accumulate in quantities sufficient to support complex atmospheric chemistry and climate regulation. The atmospheric composition continues to evolve toward greater molecular complexity as photochemical reactions driven by solar ultraviolet radiation create increasingly sophisticated chemical species through the systematic breakdown and recombination of water vapor, carbon dioxide, and sulfur compounds outgassed from ongoing volcanic activity. Trace amounts of organic molecules begin to appear through abiotic synthesis processes, representing the earliest steps in the chemical evolution that will eventually lead to the emergence of biological systems capable of metabolism and reproduction. Luna's magnetic field, never strong due to the satellite's small iron core and tidally locked rotation, begins the gradual decay that will eventually leave the moon magnetically inactive within a few 100 million years. The metallic material added during the collision with the secondary satellite creates local magnetic anomalies that will persist long after the global field disappears, providing future spacecraft with evidence of the ancient bombardment that reshaped the lunar surface during the final phase of the dual satellite epoch. The tidal forces exerted by the unified Luna on Earth's still cooling surface continue to dissipate orbital energy and transfer angular momentum from the planet's rotation to the satellite's revolution, gradually slowing Earth's spin while driving Luna's outward migration towards the orbital radius that will characterize the Earth-Moon system during its mature phase. The planet's day lengthens from the 8-hour period characterizing the immediate post-collision epoch toward the 24-hour cycle that will eventually become familiar to biological life. Solar-wind interaction with the Earth-Moon system stabilizes as Luna's post-collision orbital evolution reduces the complex three-body dynamics that previously created chaotic variations in magnetic shielding effectiveness. The simplified two-body system that emerges from the satellite merger provides more predictable protection from charged particle bombardment, allowing Earth's atmosphere to retain water vapor and other volatile compounds more efficiently while supporting the gradual chemical evolution toward greater molecular complexity. The primitive oceans that have formed in low-lying regions of Earth's cooling surface begin to show evidence of the complex chemistry that will eventually lead to the emergence of life. Though the extreme conditions characterizing these early seas continue to limit molecular evolution to relatively simple organic compounds created through lightning, ultraviolet radiation, and hydrothermal synthesis, the metallic material delivered by debris from the lunar collision adds trace elements essential for biochemical processes, contributing to the chemical inventory that will eventually support biological evolution. Computer models tracking the long-term stability of the post-collision Earth-Moon system reveal that the simplified two-body configuration that emerges from the satellite merger represents a fundamentally more stable gravitational architecture than the three-body system that preceded it. The mathematical analysis shows that this new configuration can persist for billions of years without experiencing the chaotic instabilities that drove the evolution and ultimate collision of the dual satellite system. The geological activity on both Earth and Luna begins to moderate as the thermal energy inherited from their violent formation gradually radiates away into space, allowing both worlds to develop the relatively stable surface conditions that will characterize their mature phases. Earth's magma ocean slowly solidifies into permanent crustal formations, capable of supporting continent-sized landmasses, while Luna's volcanic activity subsides toward the low levels that will persist for the next billion years, before eventually ceasing entirely as the satellite's internal heat sources become depleted. As the Earth-Moon system approaches its 25th million years of existence, the fundamental architecture that will govern its evolution for the remainder of solar system history has finally stabilized through the violent processes of collision and accretion that represent the natural endpoint of planetary formation in gravitationally bound systems. The single large satellite that orbits Earth carries within its scarred surface and complex internal structure the complete record of its formation. From the giant impact that created the original circumterrestrial debris disk through the gradual evolution and ultimate merger of the two satellites that emerged from that ancient cosmic catastrophe, the lunar highlands preserve the memory of the collision that ended the dual satellite epoch, while the dark Maria record the volcanic processes that reshaped the moon's surface during the intense geological activity that followed the merger. Together, these features create the familiar pattern of light and dark regions that will make Luna one of the most recognizable objects in Earth's sky for billions of years. A constant reminder of the cosmic violence that shaped the early solar system and established the gravitational architecture that governs planetary motion throughout the galaxy. The evidence of ancient collisions spreads across Luna's surface like a geological manuscript written in the language of impact craters and metallic deposits, preserving for billions of years the record of the cosmic catastrophe that transformed two separate satellites into the unified moon that will illuminate Earth's nights through the remainder of solar system history. Modern spacecraft equipped with sensitive instruments detect the chemical signatures of this ancient merger in the elevated concentrations of iron and nickel found throughout the lunar highland regions, particularly on the far side where the secondary satellite's fragments created the heavily cratered terrain that contrasts so dramatically with the smooth volcanic plains of the nearside Maria. The South Pole Aitken Basin stands as the most dramatic testament to the collision that ended the dual satellite epoch. Its enormous dimensions and complex structure preserving details of the impact process that reshaped both worlds 25 million years ago. Spectroscopic analysis reveals anomalous concentrations of metallic elements in the basin's floor and rim deposits, chemical fingerprints that match the iron-nickel composition expected from the secondary satellite's disrupted core, rather than the predominantly silicate materials characteristic of normal lunar geology. Careful mapping of crater-size frequency distributions across Luna's surface reveals the distinctive signature of the ancient bombardment in the form of an excess population of large craters concentrated on the far side hemisphere. Statistical evidence for an impact event unlike anything recorded elsewhere in the solar system's geological history. The mathematical analysis of these crater distributions provides quantitative constraints on the mass and velocity of the impacting debris field, allowing planetary scientists to reconstruct the detailed mechanics of the collision process through computer simulations that reproduce the observed pattern of surface modifications. Earth itself preserves more subtle evidence of the lunar collision in the form of isotopic anomalies found in some of the planet's oldest surviving rock formations. Chemical traces of the metallic meteor shower that accompanied the satellite merger and delivered exotic elements to the cooling crustal materials. The relative abundances of iron and nickel and rare earth elements in these ancient geological formations differ measurably from the ratios characteristic of normal terrestrial rocks, providing independent confirmation of the extraordinary bombardment event recorded more obviously in the lunar surface geology. The magnetic properties of lunar rock sampled by robotic missions reveal additional evidence for the ancient collision in the form of regional magnetic anomalies concentrated in areas where metallic debris from the secondary satellite became incorporated into the Moon's crustal structure. These magnetic signatures persist long after Luna's global magnetic field decayed to negligible levels, creating permanent records of the impact-induced heating and shock metamorphism that accompanied the merger of two worlds into one scarred but unified satellite. Computer simulations running the orbital dynamics of the early Earth-Moon system backward through time confirm that the observed surface features and chemical compositions could only have resulted from the specific sequence of events predicted by three-body gravitational theory. The gradual destabilization of a dual satellite system through tidal evolution and orbital resonances, followed by the inevitable collision that mathematical analysis shows must occur in any configuration containing more than two gravitationally bound objects. The crystalline structure of lunar highland rocks preserves microscopic evidence of the extreme pressures and temperatures generated during the collision, with shock metamorphic features that indicate peak conditions briefly exceeded those found in terrestrial impact structures created by much smaller projectiles. The presence of high-pressure mineral phases stable only under conditions of extreme shock loading provides direct physical evidence for the violence of the cosmic catastrophe that reshaped Luna's surface during the final moments of the dual satellite epoch. Seismic investigations of Luna's internal structure reveal additional consequences of the ancient collision in the form of asymmetric mass distributions and density variations that reflect the complex mixing of materials that occurred when metallic fragments from the secondary satellite penetrated deep into the Moon's silicate interior. The gravitational field measurements obtained by orbiting spacecraft detect subtle but persistent anomalies that trace the three-dimensional distribution of iron-rich materials throughout Luna's crust and upper mantle. The topographic relief patterns visible in high-resolution images of the lunar surface tell the story of the collision through the statistical properties of crater shapes, rim heights, and ejecta distributions that differ systematically between regions that experienced direct bombardment by metallic debris and areas that received only secondary impacts from material excavated by the primary collisions. These morphological signatures provide detailed constraints on the impact velocities and projectile compositions that characterize the merger event. Radiometric dating of lunar samples reveals the precise timing of the collision through the ages of impact melts and shock metamorphic features that record the thermal pulse associated with the bombardment by metallic debris. The concordant ages obtained from multiple independent chronometric systems confirm that the merger occurred approximately 25 million years after the giant impact that created the original Earth-Moon system. Consistent with the timescales predicted by computer models of three-body orbital evolution, the chemical evolution of Earth's early atmosphere preserves its own record of the lunar collision in the form of enhanced deposition rates for metallic elements during the period immediately following the satellite merger. When debris from the impact continued to rain down through the planet's atmospheric envelope for thousands of years after the primary collision, ice core samples from the oldest surviving glacial deposits contain elevated concentrations of extraterrestrial materials that match the chemical signatures expected from the secondary satellite's disrupted composition. Modern theoretical understanding of satellite formation and evolution provides the interpretive framework necessary to read the geological record preserved in both the lunar surface and Earth's ancient rocks, revealing how the apparently random distribution of craters and chemical anomalies actually reflects the systematic operation of gravitational forces and conservation laws operating across timescales that dwarf human experience. The mathematical models that successfully predict the collision also explain why such events represent inevitable consequences of planetary formation processes rather than unlikely accidents. The comparative planetology of other satellite systems throughout the solar system reveals additional evidence for ancient collision processes in the form of similar chemical and geological signatures found on the moons of the giant planets. Where three-body dynamics and tidal evolution have operated according to the same physical principles that governed the early Earth-Moon system. The universal nature of these processes suggests that the merger of multiple satellites represents a common phase in the evolution of most planetary systems. Laboratory experiments using high-velocity impact facilities reproduce many of the shock metamorphic features found in lunar highland rocks, confirming that the microscopic evidence for extreme pressures and temperatures accurately records the conditions present during the ancient collision. These controlled studies provide calibration for interpreting the natural experiments preserved in the geological record, allowing quantitative reconstruction of impact velocities and energy releases from the mineralogical and textural characteristics of surviving rock samples. The ongoing discovery of exoplanetary systems with multiple satellites provides observational tests of the theoretical predictions concerning three-body orbital evolution and collision processes. As astronomical surveys detect the infrared signatures of debris disks and impact-generated heating around young stars where planetary formation continues to operate according to the same gravitational principles that shaped the early solar system, these distant laboratories offer opportunities to observe the collision processes directly rather than inferring them from ancient geological records. As Earth and Luna continue their gravitational dance through space, the evidence for their violent past remains permanently embedded in rock and crater, chemical signature, and magnetic anomaly, a testament to the cosmic forces that shaped the early solar system and established the planetary architecture that governs celestial motion throughout the galaxy. The moon that rises each night carries within its scarred surface the complete history of satellite formation and evolution. From the giant impact that scattered debris across the inner solar system through the patient accumulation of orbital perturbations that drove two separate worlds toward their inevitable merger in the darkness beyond Earth's protective atmosphere. The mathematical elegance hidden within this apparent chaos reflects the deep structure of physical law that governs all motion in the universe. From the smallest atomic interactions to the grandest choreography of galaxies spinning through expanding space, the collision that ended the dual satellite epoch represents not a random catastrophe, but the inevitable consequence of gravitational forces operating according to principles established during the first moments after the Big Bang, when the fundamental constants of nature were forever fixed by the initial conditions that determined the ultimate fate of matter and energy throughout cosmic time. 4 billion years of geological time begin their patient work of erasure, slowly smoothing away the most obvious scars of the ancient collision while preserving its deeper signatures in the fundamental architecture of the Earth-Moon system that emerges from the cosmic violence of satellite merger. The intense bombardment that characterized the immediate aftermath of the collision gradually subsides as Luna's gravitational field sweeps up the remaining debris scattered throughout the Earth-Moon system, each impact adding to the satellite's mass while simultaneously obscuring the evidence for earlier impacts through the constant process of cratering and geological modification that operates across scales ranging from microscopic to planetary. Volcanic activity on Luna continues for hundreds of millions of years after the collision, driven by the thermal energy deposited during the merger and the ongoing tidal heating generated by the satellite's proximity to Earth. Massive basaltic eruptions fill the largest impact basins with dark lava flows that create the smooth plains visible from Earth as the lunar Maria, gradually obscuring the most dramatic topographical features created by the bombardment while establishing the familiar pattern of light highlands and dark lowlands that will characterize the moon's appearance for billions of years. The far side of Luna retains its heavily cratered appearance as the hemisphere most directly affected by the collision, though even these ancient impact structures undergo gradual modification through the constant rain of smaller meteorites and the slow process of mass wasting that operates in the moon's weak gravitational field and airless environment. The largest craters develop complex internal structures as their walls collapse and their floors rebound according to the mechanical properties of shocked and fractured rock. While smaller impacts gradually fill their interiors with debris and obscure their original morphologies, Earth's geological evolution accelerates as the planet's surface finally cools sufficiently to support the formation of stable continental masses and extensive ocean basins. Establishing the basic geographical framework that will govern terrestrial processes for the remainder of the planet's history, the enhanced meteor bombardment associated with the lunar collision contributes trace amounts of metallic elements to the evolving crustal composition, providing raw materials for the complex mineralogical and chemical processes that will eventually support biological evolution. The primitive atmosphere continues its gradual transformation toward greater chemical complexity as photochemical reactions driven by solar ultraviolet radiation create increasingly sophisticated molecular species through the breakdown and recombination of volcanic gases and impact-delivered volatile compounds. Water vapor begins to condense into extensive cloud systems that moderate surface temperatures through the greenhouse effect and albedo feedback, establishing the climate regulation mechanisms that will eventually make Earth habitable for complex life. Tidal evolution continues to reshape the Earth-Moon system as gravitational forces gradually transfer angular momentum from Earth's rotation to Luna's orbital motion, slowing the planet's spin while driving the satellite's outward migration toward the stable configuration that will characterize the mature Earth-Moon system. The day length increases from the 10-hour period typical of the immediate post-collision epoch toward the 24-hour cycle that will eventually become familiar to biological organisms. While Luna's orbital period extends proportionally as the satellite spirals away from Earth, the chemical differentiation of Luna's interior proceeds as the metallic material inherited from the secondary satellite continues to sink toward the Moon's center, slightly enlarging the small iron core while creating regional variations in density and composition that influence geological processes for millions of years. The ongoing volcanic activity redistributes these materials throughout the lunar crust and upper mantle, gradually homogenizing the satellite's bulk composition while preserving chemical signatures of the ancient collision in specific mineral assemblages and trace element patterns. Solar activity moderates toward the stable levels that will characterize the Sun's main sequence lifetime, reducing the intensity of charged particle bombardment and electromagnetic radiation that previously stripped away substantial portions of Earth's early atmosphere. The establishment of more benign space weather conditions allows volatile compounds to accumulate in Earth's atmosphere and oceans, supporting the chemical evolution toward the complex molecular systems that will eventually give rise to biological activity. The magnetic field generated by Earth's molten iron core stabilizes into the dipole configuration that will provide effective shielding from solar wind erosion for billions of years. While Luna's weaker magnetic field begins the gradual decay that will eventually leave the satellite magnetically inactive, the complex three-body electromagnetic interactions that characterize the dual satellite epoch simplify into the more predictable two-body system that emerges from the collision, reducing the chaotic variations in magnetic shielding that previously affected atmospheric retention and evolution. Computer simulations tracking the long-term orbital evolution of the post-collision Earth-Moon system confirm the fundamental stability of the two-body configuration that emerges from the satellite merger, showing that this gravitational architecture can persist for billions of years without experiencing the instabilities that drove the original dual satellite system toward its inevitable collision. The mathematical analysis reveals that the current Earth-Moon system represents an end state of three-body evolution, a configuration that has achieved maximum entropy within the constraints imposed by conservation of energy and angular momentum. The geological record preserved in Earth's oldest surviving rock formations begins to show evidence of the complex chemical processes that will eventually lead to the emergence of life. Though the extreme conditions characterizing the early planetary environment continue to limit molecular evolution to relatively simple organic compounds, the metallic elements delivered during the lunar collision bombardment contribute essential trace elements to the chemical inventory available for biochemical evolution, including iron, nickel, and rare earth elements that will prove crucial for biological metabolism and enzyme function. Atmospheric chemistry becomes increasingly sophisticated as the accumulation of water vapor and other volatile compounds creates the dense atmospheric envelope necessary for complex weather systems and climate regulation. Lightning activity drives a biotic synthesis of organic molecules through electrical discharge in reducing atmospheric compositions, while ultraviolet radiation from the sun provides additional energy for photochemical reactions that create the molecular building blocks of biochemistry. The lunar surface gradually develops the mature characteristics that will persist for billions of years. As volcanic activity subsides and impact cratering becomes the dominant geological process shaping the satellite's appearance. The synchronous rotation established through tidal locking ensures that the same hemisphere always faces Earth, creating permanent differences in thermal environment and geological evolution between the near and far sides that reflect the fundamental asymmetry inherited from the ancient collision. Regional magnetic anomalies preserved in lunar crustal rocks provide lasting evidence for the metallic bombardment that accompanied the satellite merger, creating localized magnetic fields that persist long after the global lunar magnetic field decays to negligible levels. These magnetic signatures will eventually be detected by spacecraft exploring the moon billions of years in the future, providing direct evidence for the cosmic catastrophe that reshaped the lunar surface during the final phase of the dual satellite epoch. The isotopic composition of lunar rocks reflects the complex mixing of materials that occurred during the collision, with enhanced concentrations of iron and nickel isotopes that differ measurably from the ratios characteristic of normal solar system materials. These chemical fingerprints preserve quantitative information about the mass and composition of the secondary satellite, allowing future scientists to reconstruct the detailed properties of the vanished world through careful analysis of the debris it left behind when gravitational forces tore it apart and scattered its remains across the lunar landscape. The crater size frequency distributions that characterize different regions of Luna's surface gradually evolve as ongoing meteorite bombardment modifies the statistical signature of the ancient collision. Though careful analysis can still distinguish between craters formed by the satellite merger and those created by the normal background of asteroidal and cometary impacts, the mathematical techniques developed to interpret these crater populations provide powerful tools for reconstructing the impact history of airless bodies throughout the solar system. Earth's primitive oceans begin to show the first signs of complex chemistry as the cooling temperatures and stabilizing atmospheric composition create environments more favorable to the formation and preservation of sophisticated molecular structures. Hydrothermal vents associated with submarine volcanic activity provide concentrated sources of chemical energy and metallic catalysts that drive the formation of organic compounds through pathways that may eventually lead to self-replicating systems capable of biological evolution. The tidal forces exerted by Luna on Earth's cooling surface continue to influence geological processes through the generation of internal heating that maintains elevated temperatures in the planet's interior, supporting the plate tectonic activity that will eventually become the dominant mechanism for recycling crustal materials and regulating Earth's surface environment. The gradual slowing of Earth's rotation due to tidal friction establishes the day-night cycle that will prove crucial for biological evolution by providing regular temperature variations and energy gradients. Solar-wind interaction with the simplified Earth-Moon system creates more predictable space weather patterns, as the elimination of the chaotic three-body dynamics reduces the complex electromagnetic phenomena that characterize the dual satellite epoch. The stable magnetic shielding provided by Earth's dipole field allows atmospheric chemistry to proceed without the disruptive effects of intense charged particle bombardment, supporting the gradual accumulation of complex molecular species in the evolving atmospheric composition. The chemical evolution of Luna's surface continues, as solar wind implantation and micrometeorite bombardment gradually modify the mineralogical composition of the lunar regolith, creating the mature soil characteristics that will persist for billions of years. The lack of atmospheric protection ensures that these space weathering processes operate continuously, slowly darkening the lunar surface and altering its spectral properties in ways that preserve information about the satellite's exposure history. Computer models incorporating the latest understanding of planetary formation and evolution confirm that the collision between Luna and the secondary satellite represents the inevitable outcome of three-body gravitational systems operating under the constraints of energy and momentum conservation. The mathematical framework that successfully predicts this collision also explains why such events occur throughout the universe wherever multiple satellites form around planetary bodies, making the early Earth-Moon system a representative example of fundamental physical processes rather than a unique historical accident. The gradual transition from the chaotic dual satellite epoch to the stable single satellite configuration that emerges from the collision marks a crucial milestone in the Earth-Moon system's evolution toward the mature architecture that will support billions of years of coupled geological and potentially biological evolution. The violence of the merger paradoxically creates the gravitational stability necessary for the long-term persistence of complex planetary systems, transforming initial chaos into ultimate order through the operation of fundamental physical laws. As geological time continues its inexorable passage, the evidence for the ancient collision becomes increasingly subtle and difficult to detect, preserved primarily in the deep structure of the Earth-Moon system, rather than in obvious surface features that erosion and ongoing geological activity gradually erase. Yet the fundamental architecture established by the satellite merger, the orbital radius annulment period, and tidal coupling that characterize the mature Earth-Moon system, represents a permanent legacy of the cosmic violence that shaped the early solar system. The mathematical elegance underlying this evolutionary sequence reflects the deep connections between gravitational dynamics, thermodynamics, and information theory that govern the behavior of complex systems operating under the influence of multiple competing forces. The transition from multiple satellites to a single unified body represents an increase in gravitational entropy that mirrors the general tendency of physical systems to evolve toward configurations of maximum stability and minimum energy. Future observations of exoplanetary systems at various stages of evolution provide opportunities to witness similar collision processes occurring around other stars, confirming the universal nature of the gravitational mechanisms that shaped the early Earth-Moon system. These distant laboratories reveal that satellite mergers represent common events in planetary formation rather than rare accidents, supporting the theoretical understanding that emerged from studying the geological evidence preserved in lunar rocks and terrestrial formations. The continuing orbital evolution of the Earth-Moon system will eventually carry Luna far enough from Earth to break the tidal coupling that currently synchronizes the satellite's rotation with its revolution, though this process will require billions more years to achieve completion. Even then, the fundamental orbital architecture established by the ancient collision will persist, providing a stable gravitational framework for whatever geological or biological processes may occur on Earth during the remaining lifetime of the solar system. The passage of geological eons transforms the violent legacy of cosmic collision into the serene celestial mechanics that will govern the Earth-Moon system for billions of years to come. As the mathematical precision of orbital dynamics gradually erases the obvious evidence of ancient catastrophe while preserving its deeper signatures in the fundamental architecture of planetary motion, 4.5 billion years from the moment when two satellites met in the darkness beyond Earth's atmosphere. The moon that rises above terrestrial horizons carries within its scarred surface and complex internal structure the complete record of satellite formation and evolution. From initial debris disk through gradual accretion to ultimate merger, Luna continues its patient migration away from Earth as tidal forces dissipate orbital energy and transfer angular momentum according to the conservation laws that govern all motion in the universe. The satellite's apparent size in the sky slowly diminishing as its distance increases towards the final configuration that will characterize the mature Earth-Moon system. The massive tides that once raised molten rock kilometers above the mean surface level gradually subside as the satellite's gravitational influence weakens with distance. Allowing Earth's geology to stabilize into the plate tectonic patterns that will reshape the planet's surface through the remainder of its geological history. The lunar surface achieves the mature characteristics familiar to future observers as volcanic activity finally ceases, and impact cratering becomes the sole process modifying the satellite's appearance. Each meteorite collision adding to the complex palimpsest of geological features that preserve 4 billion years of solar system evolution. The heavily cratered highlands and smooth volcanic plains establish the fundamental dichotomy between near and far sides that reflects the ancient collision while creating the distinctive pattern of light and dark regions that will make Luna one of the most recognizable objects in Earth's sky. Earth's atmospheric composition approaches the reducing chemistry that will eventually support the emergence of life as volcanic outgassing and impact-delivered volatile compounds accumulate in quantity sufficient to create the complex molecular inventory necessary for biochemical evolution. The primitive oceans that have formed in the deepest basins begin to show evidence of sophisticated chemical processes, operating at hydrothermal vents and in tidal pools where concentrated organic molecules interact under conditions that may eventually lead to self-replicating systems. The magnetic field generated by Earth's molten iron core assumes the stable dipole configuration that will provide effective protection from solar wind erosion throughout the planet's biological history. While Luna's weaker field completes its decay towards the magnetically inactive state that will characterize the satellite for billions of years, the simplified electromagnetic environment that emerges from the elimination of three-body interactions creates more predictable space weather patterns that support the atmospheric stability necessary for complex chemistry and eventual biological evolution. Solar activity stabilizes toward the levels that will characterize the Sun's main sequence lifetime as the stellar magnetic field develops the complex structure necessary to regulate the output of charged particles and electromagnetic radiation. The moderation of solar wind intensity allows Earth's atmosphere to retain water vapor and other volatile compounds essential for climate regulation and biochemical processes, while reducing the erosion rates that previously stripped away substantial portions of the planetary atmospheric envelope. The chemical signatures of the ancient satellite collision gradually fade from obvious detection as ongoing geological processes mix and redistribute the metallic elements delivered during the bombardment. Though sophisticated analytical techniques can still detect the enhanced concentrations of iron bitumendites, nickel, and rare earth elements that distinguish impact-affected regions from normal crustal formations. These subtle chemical fingerprints provide permanent evidence for the cosmic catastrophe that reshaped both worlds during the final phase of the dual satellite epoch. Computer simulations extending the orbital evolution forward through billions of years confirm the fundamental stability of the Earth-Moon system that emerges from the satellite merger, showing that the two-body configuration can persist through the remaining lifetime of the solar system without experiencing the chaotic instabilities that characterize the original three-body architecture. The mathematical analysis reveals that the collision effectively solved the problem of long-term gravitational stability by eliminating the excess degrees of freedom that made the dual satellite system inherently unstable. The geological evidence preserved in Earth's oldest surviving rock formations tells the story of planetary formation through isotopic ratios and trace element concentrations that record the accretion of materials from throughout the early solar system, including the exotic metallic components delivered during the lunar collision bombardment. These chemical archives provide detailed constraints on the composition and evolution of the solar nebula, while documenting the specific processes that shaped the terrestrial planets during their violent formation. Tidal evolution continues to reshape the Earth-Moon system according to the fundamental principles of energy dissipation and angular momentum transfer, gradually slowing Earth's rotation while driving Luna's outward migration toward the stable orbital radius that will characterize the satellite's mature configuration. The establishment of longer day-night cycles creates the temporal rhythms that will prove essential for biological evolution by providing regular energy gradients and environmental variations. The comparative study of satellite systems throughout the solar system reveals that the collision process recorded in the Earth-Moon system represents a common phase in the evolution of multiple satellite architectures. with similar evidence for ancient mergers found in the geological records of moons orbiting the giant planets. The universal nature of these processes confirms that three-body instabilities and satellite collisions represent fundamental aspects of planetary formation rather than rare historical accidents unique to the early Earth. Laboratory experiments reproducing the shock conditions present during high-velocity impacts provide calibration for interpreting the mineralogical and textural evidence preserved in lunar highland rocks, allowing quantitative reconstruction of the pressures, temperatures, and cooling rates that characterize the ancient collision. These controlled studies confirm that the microscopic features found in returned lunar samples accurately record the extreme conditions present when two worlds merged in the cosmic violence of satellite formation. The ongoing discovery of exoplanetary systems at various stages of evolution provides observational tests of the theoretical predictions concerning satellite formation and collision processes. As astronomical surveys detect the infrared signatures of impact-generated heating and debris disk evolution around young stars where planetary formation continues according to the same gravitational principles that shaped the early solar system. These distant laboratories offer opportunities to observe collision processes directly, rather than inferring them from ancient geological evidence. The mathematical framework that successfully explains the Earth-Moon system's evolution reflects the deep connections between celestial mechanics, thermodynamics, and chaos theory that govern the behavior of complex gravitational systems operating under multiple competing influences. The transition from unstable three-body dynamics to stable two-body motion represents a fundamental example of how physical systems evolve toward configurations of maximum entropy and minimum energy within the constraints imposed by conservation laws. As Earth and Luna continue their eternal dance through space, the legacy of their violent formation remains embedded in every aspect of their gravitational relationship. From the orbital period and tidal coupling that governed their mutual evolution, to the chemical composition and internal structure that record their shared origin in the debris of cosmic collision. The moon that illuminates terrestrial nights carries within its ancient geology the complete history of satellite formation, a testament to the mathematical elegance hidden within the apparent chaos of planetary evolution. The story written in stone and crater, chemical signature, and orbital mechanics reveals how the fundamental forces of nature operating across vast scales of space and time transform initial violence into ultimate stability, creating the gravitational architecture that supports billions of years of geological evolution and provides the stable foundation necessary for the emergence and persistence of complex systems. The collision that ended the dual satellite epoch represents not destruction, but creation. The violent birth of the celestial partnership that will govern Earth's tides and light its nights until the sun itself swells into a red giant and strips away the atmospheres of the inner planets. In the patient accumulation of orbital perturbations and the mathematical certainty of gravitational collapse, in the slow cooling of impact-melted rock and the gradual erasure of ancient scars. The early Earth-Moon system reveals the deep structure of physical law that connects the smallest interactions between individual particles to the grandest choreography of galaxies spinning through expanding space. The dual satellite epoch ends not with catastrophe, but with the emergence of order from chaos, stability from violence, and the beginning of the long geological calm that will characterize the mature solar system for billions of years to come. The ancient violence fades into mathematical memory now, absorbed into the quiet equations that govern celestial motion across the vast expanses of space and time. 4 billion years of patient orbital evolution have smoothed away the obvious scars while preserving the deeper architecture, the fundamental relationships between mass and distance, period and inclination. They carry forward the complete story of formation and collision, merger and stabilization, embedded forever in the gravitational dance between Earth and its solitary satellite. Luna rises above terrestrial horizons with the serene predictability of clockwork, its familiar face marked by the light highlands and dark Maria that record the cosmic catastrophe responsible for its current configuration. The heavily cratered far side, forever hidden from Earth's direct view, preserves the most dramatic evidence of the ancient bombardment. While the smooth volcanic plains visible to terrestrial observers reflect the intense geological activity that followed the merger of two separate worlds into one unified body. The tidal forces that once raised molten rock mountains have gentled into the subtle rhythms that govern ocean currents and atmospheric circulation. The mathematical precision of gravitational attraction, operating across 400,000 kilometers of emptiness to influence every molecule of water on Earth's surface. The extreme heating and cooling cycles that characterize the dual satellite epoch have given way to the stable thermal environment that supports liquid oceans and complex atmospheric chemistry, the foundations of the biological evolution that will eventually populate both land and sea. Computer simulations running forward through billions of years confirm the fundamental stability of the system that emerged from cosmic violence, showing how the chaotic instabilities of three-body dynamics resolve themselves into the elegant simplicity of two worlds locked in gravitational partnership. The mathematics that successfully predicted the ancient collision also guarantees the long-term persistence of the orbital architecture established by that cosmic catastrophe, ensuring that Earth and Luna will continue their celestial dance until the Sun itself evolves beyond the main sequence configuration that has supported planetary stability for billions of years. The evidence grows ever more subtle with the passage of geological time, preserved now primarily in isotopic ratios and trace element distributions rather than obvious surface features. In the deep structure of magnetic anomalies and gravitational field variations, rather than dramatic topographical relief, yet the record remains complete for those who know how to read the language written in stone and crater. Chemical signature and orbital mechanics. The mathematical poetry that connects the smallest scales of atomic interaction to the grandest choreography of planetary motion. Solar wind continues its eternal passage through the inner solar system, now deflected smoothly around Earth's stable magnetosphere rather than creating the chaotic electromagnetic storms that characterized the early epoch of magnetic field instability. The simplified space weather patterns support the atmospheric chemistry necessary for complex molecular evolution, while the moderated solar activity allows volatile compounds to accumulate in the quantities required for climate regulation and biochemical processes. The Moon's synchronous rotation maintains the same hemisphere forever facing Earth. The tidal locking achieved through millions of years of gravitational interaction now is permanent as the conservation laws that govern all motion in the universe. The distinction between near and far sides reflects the fundamental asymmetry inherited from the ancient collision, while creating the stable thermal environment that will characterize lunar geology for the remainder of solar system history. As geological eons continue their patient passage, the Earth-Moon system settles into the configuration that will support billions of years of coupled evolution. The gravitational stability emerging from cosmic violence providing the foundation for whatever geological processes and biological development may unfold during the remaining lifetime of terrestrial environments. The story written in the deep structure of orbital mechanics connects this ancient drama to the universal principles that govern planetary formation throughout the galaxy, revealing how mathematical necessity transforms apparent chaos into ultimate order through the operation of fundamental physical law. In the quiet precision of celestial motion, in the patient circulation of ocean tides, and the reliable illumination of nocturnal landscapes, the legacy of cosmic collision continues to shape terrestrial experience across scales, ranging from the microscopic to the planetary. The dual satellite epoch has ended, but its consequences persist in every aspect of the Earth-Moon relationship. From the length of days and the rhythm of tides to the chemical composition of crustal materials and the magnetic field configurations that shield atmospheric evolution from solar wind erosion, the mathematics settles into permanent rest now. The complex differential equations solve through the slow integration of geological time rather than analytical manipulation. They're solutions written in the orbital elements and tidal couplings that will govern this gravitational partnership until stellar evolution brings the entire system to its natural conclusion. The Moon continues its eternal journey across terrestrial skies, carrying within its ancient surface the complete memory of satellite formation and the promise of billions of years of gravitational stability ahead. Sleep comes to planetary systems as it comes to all complex structures in the universe, through the patient operation of thermodynamic principles that guide matter and energy toward configurations of maximum entropy and minimum potential energy. The Earth-Moon system has found its rest in the stable two-body architecture that emerged from three-body chaos, settling into the gravitational equilibrium that connects this ancient story to the fundamental order underlying all motion in the cosmos.